So we are now streaming. And I can see we don't have any Halloween costumes. Or maybe you guys are all in costumes. You're all trying to pretend to be each other. So now a new homework assignment is, how many ways can we have Halloween costumes in a class when people are trying to pretend to be somebody other than himself or herself? And you cannot have duplicates. So when you have 40 students in class, you have 40 unique costumes because everybody is trying to pretend to be somebody else, and there's no collision. No two people are trying to pretend to be the same person. That's actually pretty easy to figure out, right? Because it's the same thing as 40 choose 40 without replacement. So it's 40 factorial. It really is just 40 factorial. The person has 39 people to choose from. The second person has 38 people to choose from, and so on, which is going to be a big number. I had a Casio calculator. Okay, this is a really old calculator. And I remember 69 factorial fondly, because 69 factorial is the last factorial that my calculator can figure out, which is some normalized base 10 mantissa times 10 to the power of 98. 70 factorial would have overflown the calculator's ability. Yep. So fun stuff. All right. So how many of you have used this feature, record your name, in case you have a name that is not easily pronounced or people keep mispronouncing it? Nobody has done it? Well, I know certain people, not in this class, but I know certain students of mine who are very specific about how their names should be pronounced. So I would imagine some people would take on that and go like, yeah, use that feature. So I'm giving you guys a new homework assignment. It's due in a week. If you guys need more time, we can kind of extend the deadline. But I kind of do want you to kind of play with this, okay? This is supposed to be kind of fun. But in doing so, you're just learning how to use Prolog to do certain things. So I want you to specify a family tree and also rules to define relationships. Okay, so I'll start with simple stuff. So we start with gender statements. So this is basically saying Homer is male, and it's saying Marge is female. Okay, so you define a whole bunch of individuals, and then you assign gender to those individuals. Okay, and then we can define parenthood. So the parenthood is just this. Okay, Bart, Homer is the parent of Bart, as in Homer Simpsons, in The Simpsons, right? Okay, so you define a whole bunch of parenthood, and remember, parenthood can quote unquote stack. So you can basically use a real family tree, use fictional family tree from stories or fictions or whatever. Okay, it doesn't matter where you get your data from. If you're not very imaginative and you just go like, well, can we look at this as a tree with nodes like A, B, C, D, E, F? Yeah, we can do it that way. So you can have A as an individual, B as another individual, and so on. Okay, so that's fine. Then I want you, so these are what we call atoms. Okay, they're not atoms. These are ground rules, which means they only involve the use of elements of the universe with no variables. Because you're always saying which individual is a male, which individual is a female, and who exactly is whom's parent. So that's always just using non-variables. Then we start to get into rules. Okay, we start to get into rules of ancestry. So this has to define who is an ancestor of whom. Then you define parenthood, but this time with gender restrictions. Okay, so father of, mother of. So those are relatively easy because they are basically just referring to a particular clause and one more. Okay, you just have to add one more restriction. And then we want to define something that's a little bit even more complicated. So grandpa of, grandma of, and then cousin of. And that's it. So cousin of is the most difficult one. And I know, we have, like different types of cousins and all the removed and stuff like that. So we'll just consider all of those as cousins. That's it. Okay, just one kind of cousin to cover all the subcategories of cousins. So what is the essence of a cousin? A shared ancestor. That's it. Okay, if there's a shared ancestor between two individuals and the shared ancestor is not a direct parent, then those two individuals are cousins. Is that making any sense? Okay. So now the question is, how do we specify all of those rules and stuff like that? So you have 1 week to kind of play with Prolog and try to figure out these things. I believe there's no negation here. You don't need to use negation, which is a really great relief because negation is the one that is kind of tricky to use. Okay. So do we have any questions? Yes.
Well, what we have, like, speaking of cousins, right?
Mm-hmm.
We should have at least 2 males and 2 females, right? I mean, 2 fathers or 2 mothers. That's the preference, right?
Well, this is very open-ended, so if people want to use same-sex marriage, that's fine with me too.
No, I mean, not this way.
Oh, okay.
2 couples.
Yep.
Right?
Mm-hmm.
Like father, mother, just speaking of traditional, right?
Yeah.
Father, mother, father, mother. So
Okay.
if cousins, then we have to have like 2 couples, right?
Yes.
Um,
So if you let me see if I can show this on the tablet of a minimal tree to test all of the relationships, right? So let's see. Okay, this is from my earlier class. So let's go back, go back, go back. All right. So you will need 2 individuals as the grandparents, okay? And then actually, yeah, you would need 4 grandparents. So 1, 2. So you have 2 pairs of grandparents, and then you have this is the child of these 2. This is the child of these 2. These 2, is one set of parents, and then you still need more to define cousins. So you need another pair, possibly like that. Okay. In real life, it doesn't occur very frequently. Then you have cousins because now the offspring of these 2. So you have brothers and sisters. And now you have cousins. Yeah. Yep.
Back to negation.
Uh-huh.
Should we specify which husband is not husband to this wife or cross? So we should not have a cross-reference between.
Oh, I see what you mean.
Otherwise, all of them will be siblings.
Like parental grandfather or father's grandfather, mother's grandfather.
Well, siblings they share the same parents.
Right. If we will not specify, for example, husband Y
Mm-hmm.
is not is like husband to wife Y.
Mm-hmm.
He's not a husband to wife.
I see.
He could be in different country.
Well, it could be, but I mean, we're talking about this, not the siblings in this case.
Let me think. So if you only know about parent-child relationship and gender, can that alone be sufficient to define cousins? So that's the question. In other words, do we need to know who is married to whom to define cousins? I don't think it needs to. Because, okay, so, all right, so let's think about this a little bit. Okay, so here are 2 individuals, okay? So let's say, this is the parenthood relationship. So this is the parent of that person. This is the parent, a parent of that person. So assuming that each person has two parents, one is male and one is female, okay, in a kind of traditional sense, but it doesn't even have to be like that. So now these two parents, we just have to establish that somewhere along these two parents share the same ancestor. That will make this person and this person cousins. So I think just parenthood information is enough to establish cousin relationship. And it's the same thing for siblings too, because siblings only have to share a parent. They become then siblings. So we are not going to differentiate between half siblings versus siblings. We're just saying, okay, they are siblings as long as they share at least one parent. You first, and then you go ahead.
So do you need negation to make sure that cousins stay separate from siblings? Because if you ask if the two siblings are cousins, is that out of...
You don't need to use negation for that purpose, because you can always specify that you have one immediate. But you need to make sure that these two are not the same.
If they were siblings, then cousins would be...
Yeah. Okay. So you still need negation for that. You're right. Okay. Yep. Go ahead.
And that was my question. If there was two children on that side,
Yep.
would they be both pointed to each other as cousins also?
Yep. So you have to state that they do not have the same parent. So you still need negation, which is the backslash plus.
So we can have negation on like parents level or
Well, it may not be just a negation too. Okay. So if you look up SWI prologue, and you look up comparison, because you can use a comparison to confirm that. And there you go. So yes, we can actually use equality and inequality. So this predicate is logically sound if the arguments are sufficiently instantiated. In other words, they are not the same. X does not equal to y, and there are two different terms. The predicate fails, although there are solutions. Okay. But if you're comparing two different atoms, two different exact elements in the universe, they will tell you whether they are the same element or not. So you can use not equal to as a comparison operator to confirm that they are not the same parent. Yep. Okay. That's a good point. Good job. I didn't think of it. All right. So any other questions? Okay. So go ahead and try to do this, over the weekend, because we do have like 4 days before we meet again on Monday, and then you guys can bring your questions on Monday. Like, I can get it up to this point, but I can't figure out this part, or something like that. You're free to use Google to help you, do some research, find out, how other people do similar things. Okay, if you look up, prologue cousin, for instance, you'll find examples. Okay, so you can do that too. The point is, I just want you guys to do some research on your own, have fun with prologue, just be able to use it, define the rules, test the rules, and see whether the rule specification works or not. Is that okay? All right. Okay. Now, Prolog is an interesting programming language. You can actually use Prolog as a quote-unquote regular standard programming language. Anything you can do in C, you can do it in Prolog for the most part. It's just your program looks completely different compared to the C, C++ version. For one thing, Prolog has no loops. There's no while loop. There are no conditional statements either. So you'll have to do things to emulate a conditional statement, do things to emulate the effect of a loop, basically tail end recursion, that sort of thing. So it's a very interesting programming language. We're not going to go that far. Okay, we'll just do the ancestry, family tree homework assignment, and that will be kind of the extent of what we'll do with Prolog. Is that okay? Yep. Hmm?
Where are we going to write this? Use code blocks?
You cannot use code blocks. So basically what you need to do, the first thing is you have to download and install SWI Prolog, which I showed last time. I can include a link in Canvas. So SDBI prologue, you go to download, and here are the distributions. So you probably want to go for just the stable release. We are not using any cutting edge stuff, from Prolog. And it has different versions that you can download for Windows, for Mac OS X, and also for Linux. For Linux, for most distributions of Linux, it's just a package. You can just install in Ubuntu or Debian or any type of Debian-based distribution system. It's just a package. And I think Red Hat has it as a package as well. So is that answering your question? You do have to write your code using just a text editor. It doesn't have a built-in editor to it. So in Windows, you can use Notepad. Or if you want to download a fancier editor, you can use Notepad++. So that will work as well. Okay. Any other questions? No other questions? All right. So I'm going to leave this up for now. And then we'll move on and talk about the next main topic, which is the only thing left on the list of modules, but I'm going to add some additional ones, as we progress. This is the semester where I can actually move along the furthest, because I didn't spend as much time on propositional logic as I usually do. All right. So now we are moving back to talk about graphs. So this is the chapter that we are going to be going back to. And this one is, it is based on set theory, so we kind of have to go back and make sure that we understand all the set operations. All right, so we'll start with what a graph is, and I would interleave the discussion a lot with a tablet, because sometimes a graphical representation is a lot easier to understand. But we'll go with the text representation, and then we'll switch between the text and the graphical representation. A graph is a two-tuple, which means when you describe a graph, it has two components to it. The first component, in this case, has an uppercase V as a symbol. It is what we call a set of vertices. A vertex is also called a node, depending on the context. So a vertex or a node is simply an element, okay? A, B, C, D, E, or whatever you want to call those nodes and vertices. The set of edges, on the other hand, is a subset of the Cartesian product between the vertices. So if your vertices are A, B, C, D, E in a set, okay, then your edges are A, B, AC, AD, BB, BA, BC, and so on and so forth. It's simply a subset of the Cartesian product of the vertices. So each edge is basically a two-tuple where the first and the second item are both elements from V. But that's just coming from being a subset of a Cartesian product of V and V itself. And the order is important. So in the two-tuple of an element of E, the first one, the first element is called the tail, and then the second element is called the head, which doesn't sound, which sounds kind of counterintuitive, right? Because you would imagine the first thing should be called the head, and then the second thing should be called the tail. Well, this is where a graph comes in really handy. So we'll go to the tablet and look at the graph. So let's say we have A, B, C, D, E as vertices. So kind of imagine vertices as points in space. Edges are arrows going from one vertex to another vertex. So in this case, V as a set of vertices is just going to be A, B, C, D, E. E, on the other hand, can be empty. So right now, as it is, E is empty because we do not have any edges going from any vertex to any other vertex. So E can be empty for a graph that has no connections between the vertices. So now, let's go ahead and add some vertices into this graph. Each vertex is a two-tuple, and each item in the two-tuple is an element from V. So let's go ahead and say BA as an element of this V. So remember, B is the tail, A is the head. Why? Because this is how we draw an arrow. So when you draw an arrow from B to A, B is at the end of the tail, and then A is at the end of the head of an arrow. So that's how you remember which one is the tail and which one is the head. I typically do not use head tail to refer to the components inside the two tuple. I just say the first versus the second. Okay, so I think that's a little bit less confusing than referring to the tail versus the head. Is that okay? Yep.
Is there a direct correlation between relations and
Let me think about it. They are not exactly the same thing. I understand what you're saying, because a relation is also a subset of a set with Cartesian product with itself. So what that means is you can visualize a relation as a graph. But the intention is different. So typically when we define relations, it is usually defining a relation over a set that is usually infinitely large. So we are defining like less than, greater than, not equal to, a factor of, that sort of thing. But those usually apply to like the set of all integers or the set of all rational numbers or something like that. So it's infinitely large. But when we are dealing with graph problems, typically the set of vertices is usually finite. So it's a good observation, but they are not exactly related in that sense. Is that answering the question? Okay, yep.
And because it can point to different things, like the relation can be kind of like random.
Well, if you think about what a relation is, it really is just a two tuple. So that means you can look at this and say, oh, okay, can we look at E as a relation defined over V? The answer is yes, you can look at it that way. Can we look at BA as an element in E, saying B relates to A by the relation of E? Yes, you can look at it that way too. So from that perspective, you can kind of like you can say that edges and relations are kind of the same thing, because they are both subsets of the Cartesian product of V in this case, and in the other one I usually call it X. So is that answering the question? Okay. So very good observation because of this subset of a Cartesian product thing. So yes, that part they do share. So we'll go ahead and finish this graph here. So let's say we want to define another edge like this. So it goes from A to D. Okay. This is from D to E. And we'll have one going like this, AC. Another one like this, CD. And maybe another one like this, BC. So now we have a graph. So we have a graph that has 5 vertices. And how many edges do we have? 1, 2, 3, 4, 5, 6. So we have 6 edges in this particular graph. Are we doing okay so far, understanding what is a vertex and what is an edge? Is that okay? A lot of times, okay, if I go back to my slide here. So a lot of times we also associate a cost to edges. In other words, between an edge, a distance between edges. So it's called D. Okay. So D is a function that maps from edges as my domain to some kind of real number set. And I'm going to use a little asterisk here to basically say these are non-zero real numbers. So typically the distance of an edge, okay, from B to A is going to be a number that is non-negative. It's a real number that is non-negative. It's basically, how much does it cost to go from one vertex to another vertex. So are we good so far with that? Okay. All right, so now that we have described most of the abstract stuff, with the graph, and we'll go ahead and even add the costs of these edges too, just so that we can play with it later. Okay, so we can say the cost or the distance to go from B to A is 0.5, from B to C is 1, from A to D is 6, from C to D is 1, and then from from A to C is 0.1, and then from D to E is 2. Okay, so now I have defined, how much is it going to cost me, or what is the distance to go from one vertex to another vertex that is connected to the first one. Is that okay? So the next question is, how is this useful? I mean, we are just kind of looking at a set, a subset of the Cartesian product of the first set, and a function that maps elements of the edges to some kind of real numbers. So what exactly is useful about this really kind of abstract thing, right? So what I'm going to do next is to show you a real example where this sort of thing can be really useful. So we'll go to San Francisco. And I'm going to use San Francisco for a particular reason. Actually, downtown Sacramento would do the same, would be appropriate as well. Okay, so here is San Francisco, and we'll focus on just a small portion of it. All right, a little bit too much. We're now in the ocean. There we go. Yeah, this side of San Francisco is no fun. So we go to the other side of San Francisco. Oh, come on. And I'm doing this for a particular reason. There we go. So this is the good part. This is the part where it becomes important. I wish I could tell Google Maps not to show details when I don't really need all that detail. Okay, so this part is good. This is what I want to show. The question is, are edges bidirectional? Why are edges not directional? In other words, the edge BA is indicating a connectivity only from B to A. It does not suggest the reverse. It does not suggest that AB is also connected from A to B. Why not? Well, because in real life, we have those situations. So look at this map here. See all the arrows? So Lily Street is one way in this direction, but it's one way in the opposite direction in San Francisco. That's why. Okay? Because otherwise people will say, why don't you define an edge as a set, right? Using curly braces where the order is not important. You're just simply saying that these two vertices are connected, but in both directions. Well, that's because in real life, a lot of problems are unidirectional. Like Oak Street is only going in one direction. This is partially why it is so difficult to drive around in San Francisco. Because even though you know a place is like 2 blocks away to the right-hand side, sometimes you have to detour a whole bunch because of one-way streets. Is that making any sense? Okay, so what we are focusing on in this class are digraphs, DI graphs, which stands for directed graphs, which basically mean the edges are directional. Is that okay? Yep.
You can't just have like B, A, and D.
Exactly. If you want to say that it's bidirectional, you can always just add another edge to go in the opposite direction. But it can have a different cost or different distance. So you can have BA having a distance of 0.5 But AB, which is just reversing it, has a distance of 200. Okay, which is actually appropriate because if you think about Uber, okay, if you think about Uber or UPS or any places where they need to know how much does it cost if I go from here to here, okay, so let's think about that scenario, and you have to go from here to here, okay, which means it's against traffic if I go in this direction. Well, can I do it? The answer is yes. The big question is, what is the quote-unquote distance? What is the cost of doing it that way? So now you have to think about, what if an accident happens? What if I got caught and get a ticket? Okay? What if you get a ticket, then you have your insurance issue, right? You also have other issues stacked on top. So that becomes your quote-unquote distance. So that means if you're here and you're here, okay, going this way, you have a cost of 0.5, okay, because you're just down the street. Going this way, it's not infinite, it's just 500 because it's just a whole lot more costly. The opportunity cost, like getting caught, you're getting involved in an accident and so on and so forth, means that it is just a very expensive way to go in that direction. But you can still go in that direction. It's just a very, very expensive way to do it. Because the point is, if you want to go from here to here, you can probably just go here. This is bidirectional. Go here and then go here. So that might be just 0.1, 0.5, and then another 0.1. Okay, so it's a lot less expensive than 500. Is that okay? All right. Okay. So now we can close this window because it's actually chewing up a lot of processing time. And then we go back to the notes. All right. All right, so are we clear in terms of why we need to understand graphs, what they're representing in real life, at least in this particular example? Are we good? Okay. What else do you think is an application of graph theory? If you just look up your graph theory in Google, okay, what do you think is going to pop up? Yep. Networking. Okay, so networking is definitely one of those things because of routing, right? So if you look at routing, it is basically a huge, gigantic graph. But the interesting part about routing is the distance, the so-called distance between the edges. They're very dynamic. They keep changing over time. So that makes it an interesting problem to solve because you can not only can you figure out what is the best way to route a packet, but you can also have predictive models of what the network will look like at a certain time of a certain day. So that's kind of an interesting aspect of that. What else? What else do you think is important? What else do you think graph theory can lead to? Yep.
Can we predict or calculate efficiency or anything?
Calculate
Efficiency.
efficiency?
Or like
Efficiency of what?
probably anything.
The answer is yes. Okay. Graph theory can be used to optimize the use of, let's say, registers from the perspective of a compiler. Okay. So if you have not taken assembly programming, that's okay. You don't need to know that part. But when your C code is compiled into assembly code, how you utilize registers is a big deal. Okay. And the optimization of the use of registers can be mapped into a graph theory problem. Okay. But we are missing one that is kind of big. Okay. Yep. That too is an application of graph theory because when you have a link, then the web page containing the link is the first item of the two-tuple, and then the URL itself, or the page referred to by the URL, is the second item in the two-tuple. So now you can form a graph of references between web pages. Yep. Indexes in the database. I suppose that would be true as well. Yep. Yep. Transportation. Google Map that's exactly what it is. It's definitely an application of graph theory. But there's one that doesn't seem to be connected to graph theory at all, but it is actually a very, very big topic in computer security. What do you think it is? It's encryption. So you would think, why would encryption related to graph theory? So there are a lot of articles on that topic. We are not going to get into encryption, okay? So we are not going to study that. But there's a big connection between the two. Real graph theory is not an undergraduate course. It's not lower division, it's not upper division, it is actually a graduate level class. So if you go to UC Davis, okay, and you say, I want to take a class in graph theory, they will look at you and go like, well, are you a grad student? Because you basically have to be a grad student or get reference from a professor to get into the graph theory class. It's some heavy duty math, okay, when you actually get into graph theory. So in this class, we are just using graph. We explain what a graph is and how to use Dijkstra's algorithm and the A-star algorithm to find shortest paths. And that's about all we're going to do. But when you want to really get into cryptography, that is where you really have to understand graph theory, and it's heavy duty stuff. I took 1 semester of graph theory. I think I retained maybe 60% of the material at the end of that semester, and there's 0 left at this point. I just remember, even at a graduate level class, the professor kept saying, okay, this is the watered down version of this theorem. And oh, by the way, this theorem, we're not going to prove it in class because it will take us like 6 weeks to talk about this. So we'll just look at the actual theorem, but not really talk about the proof. That's the kind of class that it is. But it suffices to say that graph theory itself is actually very, very useful in computer science. And coincidentally, the professor who taught graph theory at UC Davis was not a mathematician, was not from computer science. He was from electrical engineering. Yeah, so interesting stuff. Yep. All right. So now that we kind of have a context of what a graph is, so we'll just define what a path is in the graph. So a path, I use lowercase p to represent it here, is a tuple of vertices. Look at it as an array, okay? Look at it as a list or an array of vertices. Edges from E must lead from one vertex to another along those vertices. So they're all interconnected by edges. So the way I express that, using the quantified expressions and stuff like that, is to say, for all I in natural number n, if I is less than bar p bar minus 1, bar p bar is really just the same thing that I borrow from set notation. It's quote-unquote the cardinality. So in this case, it is not the cardinality of a tuple. It is just the length of a tuple. How many items are in P, okay? So I is basically just saying it's an index. It's a proper index of this particular path. So the next thing is, this is a tuple. P bracket I is referring to vertex I within the tuple. And then P bracket I plus 1 is referring to the next vertex in the tuple. So these two are adjacent tuples within, they're adjacent vertices within the tuple. They're right next to each other. It has to be an element. This tuple itself has to be an element of E, which means there is an edge leading from P bracket I to P bracket I plus 1. All it is saying is the vertices have to be connected within that path. Is that okay? Okay, let's use an example to illustrate it. So in the graph that we have already constructed here, okay, one path is B, A, D, E. That's a path. Because you can find an edge to connect B to A. Well, B to A right there. You can find an edge to connect from A to D, A to D, okay? You can find an edge to go from D to E, right there. So now we have a path. Yep.
We cannot jump from straight from B to E.
You cannot jump from A to E because there's no edge going from A to E. But there are paths. There are actually multiple paths because from A to E, you can go from A to D, then to E. But you can also go from A to C, then to E to E. So you have multiple paths between vertex A and vertex E.
Basically, each path we can divide into multiple.
Yeah. Yep. Yep.
Are we going to learn about search in the deepness or search in the width of the graph?
You mean depth first search versus breadth first search? We can talk about that, okay? Now, breadth first search and depth first search. Breadth first search, we'll talk about it because that's essentially what Dijkstra's algorithm is. It's a form of breadth first search, but it's a little bit modified, so that it does it in a strange way, okay? It's breadth first search, but in the sense of, so the distance is not measured in how many hops away or how many edges away. It's based on the distance away. So it is breadth first search, but it's based on distance of the edges, not based on the number of edges. Depth first search, we can kind of explore that, but depth first search has a problem with graphs, especially graphs that has cycles or have loops, because then where do you stop, right? Then you have to backtrack and stuff like that. So we can talk about that after maybe we talk about Dijkstra's algorithm and before we talk about the A-star algorithm. Okay? Cool. So are we good so far in terms of just understanding the context of what a graph is, what it is useful for, what kind of information can be encoded into a graph? Is that okay? All right. So the next thing is, well, most of the time, when we have a graph, especially one that has distance defined, we just want to navigate. We just want to find the shortest path to go from one vertex to another vertex. That seems to be a pretty common problem that we want to solve, right? So now we want to look into algorithms that can solve that problem. There are two algorithms. One is called Dijkstra's algorithm, which is in section 4 of the notes. And the other one is called the A-star algorithm, which is in section 5. So we'll start with Dijkstra's algorithm. Dijkstra's algorithm does not rely on anything other than things that we already understand. So we have the vocabulary to talk about the algorithm already. So let's start from the beginning. Let the graph that we are trying to work on is G, and it has the vertex set V and the edge set E. And we also have D as a function. D as a function is mapping the edges to non-negative real numbers. Those are the distances of the edges. Okay, so that's basically what it says here. And then on the second line, it says we'll also define a set S as a subset of V as a subset of vertices that we designate as destinations. So that is a set of vertices where we want to be. So you go like, but why would we want to define multiple destinations? Why not just one single vertex as the destination? Well, in many problems, a lot of times, you can end up at one of the states, one of the alternatives, and it's just as good. You go like, what problem would that be? Bathroom at Six Flags. Okay? So you go like, okay, so imagine that you are, you are a parent, you have a whole bunch of elementary schoolers, okay, going to Six Flags, okay, and you're in the middle of somewhere, and then suddenly somebody says, I need to go to the bathroom. Okay? So what do you think? You pop up the map, and then you remember this class. What is the shortest path to the closest bathroom? Okay, I'm pretty sure Six Flags has a lot of bathrooms. Okay, but do you have to go to a particular bathroom? No, any bathroom would do. I just need to go to the one that is in the shortest distance, right? Using the least amount of time. I need to get to that one, because the little kid's going like, I need to go now. So you go like, okay, fine, we'll locate the closest bathroom. So that is the reason why, in many problems, you have multiple destinations. You just need to get to one destination as quickly as possible. So that's the reason why I define the set as the set of all the destinations. And they're all equally good, okay? If you get to one of those destinations, you're done. Are we good so far? All right. The other, and another example is going to be like a Roomba, okay? You're a Roomba robot, okay? You're in a huge office environment, and that's basically what automated vacuum cleaners do, because at night, you just have a whole bunch of Roombas, trying to vacuum clean and clean up the whole place. So you might have multiple chargers. So if the Roomba says, okay, my battery level is all the way down to 5%, I need to find a charge station. Does it really matter which charge station it has to go to? Not really. Just find the shortest one, go there, charge, and then go again. So same thing. Okay, so that's why it makes a lot of sense to define a set of destination vertices as opposed to designating one as the destination. Is that okay? What if your problem only has one single destination? Well, then your set S has one single vertex in it. No problem. Okay? So this is only making the algorithm more general by being able to solve more problems. Okay? All right, moving on. So these are operations. For each vertex in S, you are going to define L of V to be 0. Okay, so L of V is basically the length of the shortest path to a particular vertex. Okay, that's what big L means. So if you think about it, why do we know that the length of the shortest path to V is 0 when V is a destination? Isn't that kind of exactly? You're there already. Okay, doesn't cost me anything to go to a destination because I'm standing on a destination. Is that making any sense? So big L, just remember this, big L is the length of the shortest path to a particular vertex, or from a certain vertex to a destination, I should say. Is that okay? It doesn't matter which destination, it's just the shortest path from V to a destination. All right, what about the rest? In other words, we look at the vertex set V, and we look at the vertex set S, which is the set of all the destination vertices. What about things that are not destinations, which is in V minus S? Well, since we haven't really explored anything, we'll make an assumption of infinity. Okay, we'll just make an assumption that if V is not a destination vertex, then we assume the length of the shortest path from V to a destination is infinity. Okay, because we don't know anything at this point. Is that okay? All right. And then we'll also define a set Q. So this symbol here it just means assignment. Okay. In other words, we are creating a new set Q, and we copy everything in S to Q. Is that okay? So in C and C++, it is simply Q equals S. It's an assignment operation. Are we good so far? All right. And then we define E prime as an empty set. So E prime is an empty set, and this is what I call the set of solution edges. Okay, these are the edges in the solution. So we are constructing E prime as we execute the algorithm. Are we doing okay so far? So how many things do we have? Okay, we have quite a few items here. We got the graph itself. It is a two-tuple, it contains the set of all the vertices and the set of all the edges. We have a function d that tells us what is the cost of an edge. We have a subset S, which is the set of all the destination vertices. We have a L function, which is basically the length of the shortest path from a vertex V to a destination. Okay. We have Q, which is a set of vertices that we should look into, okay, quote unquote look into. And then we have E prime, which is the set of all the solution edges. So those are all the pieces that we are dealing with here. Not all of these pieces are going to change, okay? Many of these are constants, they do not change. V does not change, E does not change, D does not change. S itself does not change either. L will change over time, okay? Will change will change the length of the shortest path from a vertex to a destination as the algorithm executes. So L does change, Q does change, and E prime does change. So we have three things that will change as we execute the algorithm. L changes, Q changes, E prime also changes. The rest are constants. So here's the algorithm. So I'll describe the algorithm first and use and also use the English part of the description. So the algorithm says as long as Q is non-empty, do the following. As long as we still have elements in Q, we have to keep going. Okay, we have to perform another iteration. The first thing we do in an iteration is we're going to select a particular element in Q such that blah 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 blah. Okay, so what does that mean? Okay, we'll read it out loud first, and then we'll try to figure out what that means. So we're going to pick out a V from Q such that for all W in Q, L of V is less than or equal to L of W. What is that saying? V currently has the shortest distance, or the shortest path from V to a destination is the shortest amongst all of the vertices in Q. That's basically what this part is saying. Is that okay? Let's think about it a little bit because I want you guys to understand the notation. Yep.
Basically, it looks like in Google Map, you set the destination point. The Google Map just gives you a couple of routes.
Mm-hmm.
And basically, V is the route 1 and W is route 2. And when V is less than W or L of V, that means it's the shortest.
Okay, there's another way to look at V, okay? You can look at V as the most promising vertex because it is the vertex that has the shortest path to a destination at this point. Is that okay? Okay, so later on when we run that example using the graph that we have constructed, we can take a look at it. So basically at this point, well, I even use those words here. So V is the most promising vertex within the set. So we pick it out and go like, okay, since you are the most promising one, who else is connecting to you? Is that okay? So because I'm the closest one to a bathroom, okay? So now people go like, oh, tag, you're right next to me, and you're the one who knows where the closest bathroom is. Tell me where the bathroom is, so that I can go to you first, and then from your location go to a bathroom. Is that okay? Yep.
Dijkstra algorithm increases when you find the best path. So you go all the way to the node right before to find the best path, come back.
Mm-hmm. It's kind of like that. So let's say we have two vertices in Q. So you're one vertex, I'm one vertex, okay? So you're advertising to the whole road and go like, from my location, it's 500 yards to go to the closest bathroom, okay? And then I'm at the other vertex in Q, and I'm saying, well, from my location is 20 yards to go to the closest bathroom. Okay? So now the question is, well, which one should we explore first? Well, should we explore the vertex that is known to be further away from any closest bathroom, or should we be greedy and start with the vertex that is already known to be closest to a bathroom? Well, Dijkstra's algorithm is what we know as a greedy algorithm. It just starts with the one that is closest, because there might be a vertex that is equal distance to us. Okay, so there may be a vertex that is like 100 yards from me and also 100 yards from you. So by looking into me first, that vertex that is 100 yards from both of us will find the shortest path by going through me first.
So, speaking of greedy,
Mm-hmm.
we first check if we're not there yet.
Well, that's the thing about Dijkstra's algorithm. Dijkstra's algorithm does not just find the shortest path from one vertex to one of the destinations. It finds the shortest paths of every vertex to the closest destination. At least this version does. Now, that is kind of cool in many ways, because by running this algorithm, you are not only finding one single shortest path from one vertex to its to the closest destination. You are actually finding the shortest paths of every single vertex to a destination. So that is kind of cool, from the perspective of this algorithm. Okay. All right. So what do we do next? Now that we have selected a V, so the next thing is we do this. We are changing Q. We are saying let's remove V as an element from Q, because I'm going to look into it. Okay. So Q is basically maintaining a set of vertices that is quote unquote worthy of looking into. So now that I have selected V to look into, I remove it from the set so that I don't keep looking into the same vertex over and over again. Then we have a for each loop. So this for each loop here is just picking out every single edge that is going into V. So all the incoming edges into V, we're looking at every single one of those. Okay? So you can kind of imagine in the example, I'm the one, within Q that knows the shortest path to a bathroom. Okay? So what we are doing now is we turn around and go like, okay, who else is, going in the direction of tech, or has a path to go to tech? Is that okay? Because now they can go through me to go to the bathroom. They can go to my location, and then from my location they can go to a bathroom. And because the distance between me and the bathroom is known to be the shortest of all the vertices in Q already, so these vertices is promising to go to my location first to go to a bathroom. That seems to be going to kind of get to the shortest path. Is that making any sense? Okay. So W is basically just a vertex that is connected to V, and we need to look into W and go like, well, is there anything we can do with W, the vertex? The first thing we do is we assume that this is E, because we can just find the distance E here. So WV is a two-tuple representing an edge. And then the conditional statement is really the key of the entire algorithm. So we look into this conditional statement here, and we ask, what does that mean? Well, V is me, okay? I'm 20 yards away from a bathroom. And W is a vertex that can come to my location. Okay? So now we say, hey, W, what is the length of the current shortest path from W to a destination? Okay? W says 50 yards. Okay? And now we have to take into consideration and say, okay, now let's see. W, in order to go from W to V, what is that distance? So the draw is 30 yards. Okay? So let me represent it. The length of the known shortest path from W to a destination is 50 yards. The length of the shortest path from me to a destination is 20 yards. The break-even point is from W to V is 30 yards. Then it's a break-even, right? Because if it cost, if the distance between W and V is 30 yards, then it's the same. Okay, the current shortest path of W is 50 yards away from a destination, but if we go from W to me and then to a destination, it is also 50 yards. So it's break even. So whether we change the path or not with W, doesn't change a single thing. Is that okay? Is that making any sense? Okay, so let me see if I can use a graph or graphical way to represent it. Okay, I'm going to use a new graph here. So we have a W, we have a V, and then we have some destinations here. Okay, so we know that from V to one of these things, okay, this is a path, but the length of V is 20 yards. We know from here through the current known shortest path is 50 yards. Okay, so now the question is, we know W goes to V. We know that already. So if this edge has a distance of 30 yards, then it is a break-even case. Whether W goes through its currently known shortest path, or go to V first, then go to a destination, is the same. Okay, it's still a distance of 50 yards. Is that okay? Which means, why change, if they're the same? Okay, fine. So that means if this number is 30 or more, we don't want to change. But if this number is like 29, anything less than 30, then it's worth the change. Because now we can say, hey, W, the shortest path that is known to you up to this point has a distance of 50 from a destination. But guess what? If you go to V first, then you go to the shortest destination, it will only cost you 29 plus 20, which is 49 units. So now it has found a shorter path by going through V to a destination. Is that making any sense? Yes? Okay. So if that is the case, then the condition is going to be true. So the condition of L of V plus D of E, which is WV, is less than L of W. We have just found a new and shorter path from W to a destination. Is that okay? Yep. Yes. In order for this to be worthwhile. Yep. All right. So now that we have found a shorter path, what do we need to do? What do we need to update here? Well, the first thing we need to update is L of W itself. So L of W in our example is going to be updated to 49. We basically say, hey, W, vertex W, the length of the shortest path to a destination is no longer 50. It is now 49. We just found a shorter path. The next line is kind of confusing. What it's doing is, in the solution graph, all the outgoing edges of W need to be removed because they were misleading. Is that okay? Because every outgoing edge of W from W is a part of a solution graph. But that is also going to be on what we thought was the shortest path, which is now proven not to be the shortest anymore. So now we have to remove all of those edges. And then what we do is we add it back. We add it back on the next line. So E prime is now E prime union with a singleton set with only WV in it. Because that's the edge that is going to help W go through V to go to a destination. Is that okay? And then what do we do? Well, what do we do with W? Well, before we are all kind of happy and say, hey, W got the shortest path already, but now we are not so sure. Because when we change W, what about all of those other vertices that go through W to go to a destination? Don't you think we might need to update those guys too? So what do? we put W back into Q and say, let's reconsider those vertices. Is that okay? That's really the essence of Dijkstra's algorithm. Okay? And when this is all done, when this for loop is done, we go back to the main while loop. When the main while loop is done, then the new solution is V comma E prime. E prime would be the edges of another graph, which I would call the solution graph. Yep.
What if there's no path between connecting those edges?
It would just pick one of those two.
So what if there's no path between?
If there are no paths, oh, okay. So if there are no paths between two vertices, then L is going to be infinity. The L value is going to be infinity because you don't get to touch it.
So they're all initialized to infinity?
They're all initialized. All the L values are initialized to infinity. Yep. So are we doing okay so far with the concept of the algorithm? Yes? Maybe? Sorta? All right. So maybe what we need to do, and I think we got enough time, we got 10 minutes, is to trace this through using the graph that we have constructed earlier. So we'll look at this graph. I'm putting it at the bottom so that I can get some room on the top for the actual trace. And we'll borrow a spreadsheet from earlier. Okay. All right, so let me think. We know for sure that we have to look at Q as a set. We have to look at V because that's the vertex we have selected from Q. We have to look at W, which is an incoming edge, or the WV is the incoming edge that we need to consider. Let's see, what else do we need to know that is not in the graph itself? The L values, right? So we have the L values of each one of those items. So we have L of A, L of B, L of C, L of D, and then L of E. All right. And then E prime too. Okay, we forgot about E prime. So where should I put E prime? I'm shrinking the columns first so that we can fit everything on the screen. So we'll put E prime here. Insert to the left. There we go. So now we have E prime. Okay. V is easy to look. We can look at the graph and know what V is. E is also there, and same with D. So that's why I'm not using the spreadsheet to represent those, because I wouldn't have enough space to do it. Okay. So we'll first do some initializations. So the initialization is all of these L values will start with infinite unless we know what is the starting point. Okay, and I haven't really designated a starting point yet. I think E makes sense to be the destination. So we'll just make that assumption here. So let me write it down. S is just E itself. There we go. Okay. So that means L of E is a 0, but everybody else is infinity. That's how the algorithm initializes all the L values. Okay. Q is the same as S, so it is a set with only E initially in it. And then E prime is an empty set to begin with. So that would be the initial condition when we start the algorithm. We go into the first loop. The first thing we do is to say, okay, what is the vertex that has the the length of the shortest path is the shortest, is the smallest amongst all the vertices in Q. That's a really stupid question to ask because Q only has one element, right? So there's really no minimum to say in that case because it only has one element. So we say, okay, let's pick E, and then we have to remember to remove E from Q, once it is removed, like that. Okay. And then we have to look at all the incoming edges to E. Well, E only has one incoming edge. It is from D. So W is basically vertex D now. And now we have to do some calculations. So the calculation that we have to do is to say, okay, W, what is the length of your shortest path to a destination right now? Not W, but D, okay? So if we look at this and go like, L of D is infinity, okay? The length of the shortest path from D to a destination right now is infinity. Okay. What if what if you go through V to go to a destination? Well, if you look up E, it has a L value of 0. Oh, okay. What about the edge? What about the cost to go from D to E? It's only 2. So 0 plus 2 is 2. And 2 is less than infinity. So now we go like, oh, great. We have now found a new shortest path from D to a destination. So we update this guy to be 2. And then we also have to update a few things now, because we have to update Q to include D, so that we remember everything that goes into D may need to be updated now. And we also have to update E prime, because the edge going from D to E is part of the solution now. Is that okay? So now we go back to the outer loop, because we're done with the inner loop. We go back to the outer loop. The outer loop asks, is Q empty? Nah, Q is not empty. It has got one element in it. So since it's only got one element, I don't really have to choose, because hey, if it's the only element, it's going to be the element that looks the most promising to me. Okay, so that means we pick vertex D as variable V, and then we remove it from Q, so Q is now empty again. And then we have to say, okay, what edges are coming into D? Okay, what vertices are connected to vertex D? We got 2 here, okay? We got vertex A, and we also got vertex C. Well, doesn't really matter which one, because we have to look at all of them, okay? So we'll just say that, let's pick A first. So A is the first one that we consider as W. And then we say, okay, are we finding a shorter path from A to a destination? So we first have to ask A, what is the length of your shortest path at this point to a destination? A says, well, it's infinity. Okay. What if vertex A is to go through vertex D to go to a destination? Vertex D is only 2 yards away from a destination, and then the edge going from A to D is 6. 6 plus 2 is 8. 8 is less than infinity. Okay, we found a shorter path. So now we go update the L value of A to 8. And then we have to add A to the set Q. And we also have to add that edge to the set E prime. So that edge is going from A to D, like so. Are we doing okay so far? Okay. What is the other edge going to D? C. Oh, okay. So let's look at C. So we look at C, and then we do the calculation, in the conditional statement, and we ask, are we finding a new shortest path for C to go to a destination? Let's see. The length of the shortest path from C to a destination is currently infinity. Okay? But if C is to go through D to go to a destination, then it will be just 1 plus 2, which is 3 units. 3 is less than infinity, so let's go ahead and update it, because we just found a shorter way for C to go to a destination. So we now update L of C to 3, and then we go back here, we add C to the set of Q, but we also add that edge. DE is still here, AD is still here, but now we also have to add CD as an edge into the E prime set. So E prime is going to get a little bit bigger as we add more stuff, but these two should be pretty narrow, so let's go ahead and make sure they don't take up too much space. All right, so now we are done with the for each loop, and then we go back to the for loop. The for loop says, Well, is Q empty? Nope, Q is not empty. Which one is the most promising out of A and C? Well, you look up L of A, it's 8. L of C is 3. Ah, C looks more promising. So since because the Dijkstra's algorithm is greedy, then it goes for the one that looks the most promising first. Okay? So that is why in the next iteration of the while loop, we pick C as the one to explore. And then we have to now look into, forgetting to remove it from the set queue. There we go. So now we have to look into all the incoming edges to C. There are two. There's A and then there's B. Okay? We can look at A first. Okay? So we look at A first, which means here we consider A as variable W. And then we ask that question again. Okay? We say, are we finding a shorter path for A to go to a destination? Okay, let's figure it out. What is the length of the current shortest path from A to a destination? 8 units away from a destination. What if A is to go through C to go to a destination? 3 plus 1, which is 4. Oh, we found a shorter way to do it now. Cool. So now we can update L of A to 4. Oh, this 0.1. Yes, correct. Sorry. So 3 plus 0.1 is 3.1. Oops, wrong place. There we go. 3.1. So we update the L value of A to be 3.1 because that is now the length of the shortest path from A to a destination because it's going through C. Is that okay? This is the tricky part of Dijkstra's algorithm because it can go back and update something later on. All right, well, if we do something like this, we better add A back into the set of Q. But it's already in there. That's fine. Not a problem. But now we have to go here and say every outgoing edge of A has to be removed. So AD now has to be removed. But we're going to add back AC to that set. Okay, so I can break it up into 2 operations, but I can also use fonts to indicate what we are doing to the set. Okay, so I would try to do it with fonts. So use a cross out or strike out font. I'm not sure whether it will let me do it because this is a spreadsheet. But we'll give it a try. So highlight this portion, go to format. Okay, character. Huh? Sorry? Say again? Oh, okay, I see. In text, strike out. There we go. Nice. So now it is clear what we are removing, and the last one is added into it. Cool. Oh. Let's see what time. We're out of time, but that's okay because the way I trace algorithms like this means we can pick it up on Monday easily, as long as I remember to save the file. All right, I'll see you guys on Monday and work on that Prolog program. You can use Google search, okay? So you can find the syntax, you can find some clues of how to do it. The idea is, just kind of try to learn it on your own. I know you guys can do it.
Did you take roll today? I came in a little late.
I did not take roll today.
Okay, cool.
Okay.
I have a question regarding the prolog assignment. So for the prolog assignment, are we going to be looking for like siblings, niece, and not niece, like cousins?
Just cousins.
Just cousins?
Yep. So no gender, huh?
Are we looking at any other relations like testing for?
Like
Like let's say like a grandparent to like a grandson or arguably.
no grandson, but there's grandpa and grandma.
Okay.
Yeah. turn off the mic, during the 5-minute break?
No, I need to separate classes.
Oh, you have to rename it, so it reads correctly. All right, so now it's recording. All right, so last time, we were talking about how procrastination is actually a good thing, because because we were talking about, how, I just want to look at the big chunk of codes, so instead of, actually specifying the logic of how to find a prime factor f of n, I just said, well, assuming there is a way to find a prime factor f of n, we'll use it, okay? So in other words, the key here is I specify what it needs to do, but not how it is going to do it. So it is very important to separate the what from the how. How is lower level detail, and then the what is a high level description of, or high level view of what that line really means. Is that okay? All right. So that's kind of important. So now the question is, well, that turned out to be a bad assumption. In other words, when you look up the libraries of most programming languages, they don't have anything that help you find a prime factor f of n. So now what do we do? Okay? So now we have to figure out how to find a prime factor f of n. But my problem is now smaller. In other words, the original problem is, how do I find all the prime factors of a particular number? That's a bigger problem. But my current problem is now a smaller problem, because now I only have to worry and say, well, I'm not finding all the prime factors. I'm only finding one prime factor of a particular number. Is that okay? So that's a smaller problem that I need to solve. And last time I started this, but I did not finish it, which is basically the approach of, but how do we figure out the pseudocode to do something? Okay? And if you remember last time, we had a spreadsheet, okay? And I picked some kind of big number to start with to find a prime factor of. So we'll kind of do it today again. Okay, so today we'll do exactly the same thing, because I want you to be able to visualize, the approach of doing things. So what we'll do is we say, okay, we have a number n, and we have potential factor f. And this time we'll once again use a bigger n, because if I pick anything that you can just eyeball and say, oh, I know a prime factor of this number, then it's not going to work, because it's not going to force you to use a systematic way to solve that problem. So we have to start with a problem that you cannot just eyeball and go like, yep, I know, that is a prime factor of this number. So we'll once again try some kind of randomly big number. So let me check this one and see whether that's going to work or not. Yep, that might work. Okay. Because all of the obvious rules do not apply. Okay? It's obviously not divisible by 2. It is not divisible by 3, because when you add up all the digits, the sum of all the digits is not divisible by 3. It's not divisible by 5, so 7 is the first chance. Okay, so it's definitely not obvious. So the first factor we'll try is 2. Then go like, well, but didn't you just say that 2 cannot be a factor? Well, to us, it is obvious. Okay, because we use base 10, and since many, many years ago, we learned all of these rules of thumb, right? To say that, oh, okay, if the least significant digit is not an even number, the number itself cannot be divisible by 2. We learned all of those rules of thumb. But those rules of thumb only apply in base 10. Well, the computer does not use base 10 to store numbers. So that means a lot of the rules of thumb that we are used to really is not easy to code in a computer program. You can do it, but it's not worthwhile. Okay. So now we have to actually go through the logic of doing this. So now we basically say, what is n mod f? Remember what mod is? Mod is kind of like division, except you're tossing the quotient away, but you're keeping the remainder. So n mod f is the remainder of n divided by f. Mod itself stands for modulus, by the way. Okay? All right, so we'll use the spreadsheet to help us do this computation. So this is just the mod between n. So n is $2, because I don't want the row number to change. And then f is b2. Okay, there we go. So we now find that the remainder of this number divided by 2 is 1, which is not surprising. We kind of know that already. And we also now want to know, should we stop? Okay, so we'll just say, should we stop? Okay, well, how do I know whether I should stop or not? There are two reasons for me to stop. One is if I confirm that n is a prime number, I can stop. Because it's a prime number. It is its own prime factor. If I find an actual factor other than n itself, I can also stop. So I got two reasons to stop. So now we have to code those two reasons. So instead of coding those two reasons as one single reason, let's break it up into two separate reasons. Okay? So the first one is to answer this question, is f a factor of n? Okay? And how do we answer that question? Do we have enough information here to answer that question? What do you guys think? Exactly. So if n mod f is 0, then we can confirm that f is a factor of n. Then we can stop. Okay? So we'll use a spreadsheet to help us calculate that. So we'll say if this number is a 0, then the answer is true. Otherwise, the answer is false. Now we can use just a comparison to do it as well, but I'm using a conditional statement here. Okay. So we can now go work on the next row, which is this potential factor plus 1. And the rest, we can just kind of copy. Like so. And now we can copy the entire row just a few times. Okay. All right, so far we haven't really confirmed that we have found any factors yet. Okay. Do you guys remember from last lesson or from the previous class? How can I tell that n itself is a prime number? Do you guys remember the square root thing? Yep.
If a value of f greater than the square root of n is not a prime factor.
Yep. Okay, so that means we cannot find any factor that is not n itself. Okay, very good. So we can now say, is n prime? Okay, that's the question. Question mark right there. Okay, and to answer the question, we have to say, well, let's think about the squared of f. Okay, so we say if this number times this number, instead of using square root, I'm using a square. So if this number is greater than, oops, okay. No, I'm not done yet. Okay, if this number is greater than n, which is $2, then we say true. Otherwise, we say false. Okay, so all of these is false. Okay, so now what we need to do is really just to copy and paste all of these rows until we find the answer to this question. So we keep going. So we have to know approximately when to stop. The number was 90,000 something. So if you think about it, 300 times 300 should be about where we need to stop. So at the most, we need about 300 rows to get this to work. 300 something. 307, thank you. There we go. One more. Yep, excellent. All right, so now we need to go back and say, well, did we find a factor before we confirm that that number is prime? And so far we haven't found a 1 in column D. Oh, there you go. So we found one. Yeah, there you go. All right, so we confirmed that 43 is actually a factor of that number that we found. Okay, so, but you're not going to use a spreadsheet when you're writing a program. Okay, a spreadsheet is a really good way to visualize what your program needs to do, but we are not using a spreadsheet to plug into a program and say, okay, refer to that spreadsheet to solve this problem. But we can now look at this spreadsheet and go like, how do we know when to stop? In other words, if I change this number to something else, okay? Let's say we change it to a relatively small prime number, okay? 137, is that a prime number? Seems prime to me. So if we plug in 137, and then we go like, where is it going to say true? Right here. So with this one, because 137 itself is a prime number, we can kind of confirm that it is a prime number because we have just tried 12 as a potential factor. 12 times 12 is greater than 137. And since we have not found a factor before this point, we can now confirm that it has no other factor than itself. Okay? So there are two reasons that we can stop. Either we have found an actual factor that is not n itself, or we confirm that n itself is prime. Those are the two reasons how we can stop. Is that okay? And then when you look at this, you go like, well, when we stop depends a lot on what number we are dealing with. Because if we plug in a very simple number like 6, we stop right away. Because 2 itself is a prime factor of 6 already. So now in your mind, you have to come up with a question. Because every time you write a program and you want to figure out how do I get started with a program, you have 3 choices. The first choice is a sequence. The second choice is a conditional statement. And the third choice is a loop. Those are the 3 main control structures that you can consider. A sequence means there's only so many steps of assignments that you can perform. Okay? Do you think this problem can be solved with a fixed number of assignment statements? No. Probably not. Okay? It seems like there's some testing around, and also the number of times we have to do this is kind of variable. So that means a sequence of assignment statements is probably not going to do the trick. Okay. Second control structure, conditional statement. A conditional statement or a structure of conditional statement is basically saying we have these many branches, okay, and we can use conditions to help us steer to one of the branches. Then we choose one branch to execute, and we are done. Do you think this problem can be solved that way? But do you know how many branches you would need if I don't give you a range of number to begin with? You don't, okay? So that means the branching method is not going to be a practical method. It can be done, but it's not practical. Okay, so if that is not going to work, we only got a loop left, okay? So what a loop does is to suggest that there's repetition. Something is being done repetitively. Is that okay? What do you think in this spreadsheet suggests something is being done repetitively? Yep.
I would say while the E column is false, keep doing a bunch of statements that checks if the n mod f equals to 0.
But what is giving away that we need a loop here? Aha. Okay, so what you're saying, if I understand you correctly, is column B. If you look at column B, the value of the potential factor is 2, 3, 4, 5, 6. It is very, very regular. Okay, there's a pattern to it. The other columns, there's really not a whole lot of pattern to it. If you look at column C, which is computed, it doesn't seem to have a whole lot of pattern to it. If you look at column D, it is computed as well. Column E is also computed. And in fact, with column D and E, we basically say, if it is a 1 or true, we get out. Okay, so you can't really look at that as a pattern. But column B is a very strong indication that this is a loop, because we are looking at the particular value that is really easy to compute from its previous value. Is that making any sense? Okay, so what I usually do is I try to sum this up as a way to write a program. So what we need to do now is to say, I think we got a loop, okay? So you basically just say loop and loop, okay? There's no such control structure as a loop and loop, okay? I'm only using this to basically say, I think we have a loop in here. Is that okay? And then we'll refine it until we get to either a while do loop or a repeat until loop. But at this point, we just know it is one of the two, not quite sure which one. Okay. So whenever you have a loop, you have two additional questions to answer. One is, what are you doing in the loop? What is being changed per iteration? And then the second question is, when do you stop? When do you get out of the loop? You can answer one or the other question first, because the answer of one or the other question will help you answer the remaining question. Is that okay? So, okay, so let's go back to the spreadsheet, and you go like, what is being changed on a per row basis that is really easy to figure out? It's like, I can see the pattern.
Per iteration, you're
Increasing f by 1, okay, per iteration. Okay, so let's put it into the loop here, and we say, okay, we know that this is a loop, and then for each iteration, we are adding 1 to f. Are we doing okay so far? So far? So we're making an observation of based on the table, and then we say, okay, we know how to change f from one row to the next, okay? And we know it's being done repetitively. So now the remaining question is, well, it has to stop at some point. When do we stop? So we go back to the spreadsheet, and then we run through a few examples, okay? So with 6, we are stopping right away because 2 is a factor of 6. And how do we know that? It is because n mod f is 0, okay? Let's try something else. Let's try 91, okay? 91 is not a prime number because it is divisible by 7. So with this one, we go through 2, 3, 4, 5, 6, and then by the time we get, when f equals to 7, then we exit the loop because once again, we confirm that 91 mod 7 is a 0, is true. Excuse me, okay, I take it back. 91 mod 7 is a 0, that is true, and that's the reason why we are getting out of the loop. Okay, and then we try something else. And then we can try a prime number. 97 is a prime number. And then this time we look at this and go, oh, we stop only here. We only stop at this point because 10 times 10 is greater than 97. And that confirms that 97 itself is a prime number, and that's why we stopped. Is that okay? So the reason why we stop, if I go back to the pseudocode here, and we can just kind of loosely describe when we need to get out, and then we say exit when. If you prefer to use like just a description, that's fine, because we can refine this step by step. So we can say when f is a factor of n, or n is confirmed a prime number. Okay, this is my first iteration of my attempt of the pseudocode. In other words, I'm not going to write the entire pseudocode in one shot, okay? I'm just going to get some ideas, get a rough sketch, and then we'll refine this, and then we'll refine it some more, and then we'll refine it some more, until we get to the point where, okay, I think this is it. This is actual pseudocode, okay? So in the second iteration, then we go like, well, let's try to figure out what this means, okay? F is a factor of n. How do we know that f is a factor of n? The mod operator is useful, okay? So we go like, we can now say this is n mod f equals to 0, because that means n is a multiple of f, and which also means f is a prime, is a factor of n, so we can get out. All right, so that's my second iteration of the attempt. So each iteration of the attempt to write the pseudocode doesn't do a whole lot. It just do a little bit of the coding. So on my third iteration, I go to the other condition and go like, how do I confirm n is a prime number? Using the trick that we talked about last time. The other way around. F squared is greater than n. Okay, so if f times f is greater than n, then I have confirmed that n is a prime number. Is that okay? More or less? Okay. All right. So this is my third iteration. So at this point, I look at this code and go like, well, all the simple stuff is already done in pseudocode. So it's time to really think about, should I use a pre-checking loop, or should I use a post-checking loop? So the real question is, do I need to increment f at least once? That is the question. Well, that brings up another question. What is the first value of f? Is that making any sense? So we have to think about the initialization problem, which is, well, we refer to f, we keep incrementing f, but what is the first value of f in order to run this loop here? Well, we got two possible answers, because you can initialize f to 1, go through f gets f plus 1, and then test the condition. Or you can initialize f to 2, and then use a pre-checking loop so that you test the condition before you increment it the first time. Do you guys see what I mean by that? So let me show you the two alternative codes. They're both quote-unquote correct. They'll both get the job done, but they are different. So the first one is using a while loop that says, okay, now remember, if you use a while loop, the exit condition has to be inverted now, because now we are trying to specify the reason to stay in the loop instead of the condition to get out of the loop. So we have now to invert this condition. The laziest way to do it is this. Look, I'm using C syntax here. No. So switching back to pseudocode syntax. So we're just inverting this, okay, which is fine. There's no problem doing this. And to do this, we have to initialize f to 2. And then inside the loop, we're still doing pretty much the same stuff, which is just adding 1 to it. So f gets f plus 1, like that. That will work. Okay, no problem. But we have an alternative. So the alternative is to initialize f with 1, and then we use a repeat until loop. So with a repeat until loop, f gets f plus 1 is inside, and then the until condition is the same as the exit condition. Because in the repeat until context, you are specifying the condition to get out of the loop, so it becomes the same thing as the exit condition. So when you look at these two versions of the same code, they will both get the job done. So now the question is, well, if they can both get the job done, which one should I use? So you look at, let me emphasize what the problem is. Should I use this piece of code, which works, or should I use this code, which also works? They work pretty much the same way. In terms of execution time, one is just a little bit slower, but not by much. So we'll just say that they are, in terms of efficiency, they are the same. But which one should you use then? What would be your evaluation criterion in this case to determine which one to use? The second one? Do I hear the first one too? Okay, so we have someone saying the first one and some people saying the second one. So why would you choose the first one?
The first one, just because it's easier
And
to read in the sense that like range, it just seems a lot more illegible. Secondly, what I would do is like isolate, like I would want the while condition up there, like what's the last resort statement, in the sense that like you would want that program to keep running until like s squared is greater than n is starting to prove true.
so you want to spread the negation to the inside.
Yeah.
So it's not a negation on the outside of the OR.
Yeah.
Okay. But in terms of the control structure, you prefer the while.
Yeah.
Okay. And some people prefer the repeat until. So any particular reason? Yep.
I think the second one is easier. And the value of f is not going to change after you find the prime number or the factorial.
Mm-hmm. Okay.
As soon as you find the solution, it's going to leave the loop.
Okay.
It's not going to go back and change the value of f.
Okay. So are there any other comments? Does anyone want to add anything to the evaluation? No, nobody? Okay. So they're both equally correct in terms of just correctness, in terms of the behavior. Personally, I would prefer the first one. Now, the reason why I prefer the first one is because it is clear that the first f that I use to test as a factor is 2, because 2 is actually spelled out as the initial value. Now, with the second loop, you can follow the code and say, oh, okay, first of all, f was initialized to 1, and then it has to be incremented before we get to check it. So the first f that we actually check actually has a value of 2. That is not direct. Okay? It is a little bit indirect, which also means, if you're not careful to evaluate what you're doing inside the repeat until loop, then you may not, remember that the first value that you're testing is not 1, but 2. Now, the other reason is also, what if, so in general, okay? So in general, what if you have more things to do inside the loop? It is not a one-liner. Instead, it's like 20-liner. Well, then it becomes a much more difficult problem with a repeat until, because now you have to read through all those 20 lines to figure out what is happening to f before you can decide what is the first value of f that I'm using to evaluate the condition. As opposed to the first approach, okay, we stick a value of 2 into f, and then we immediately use f to evaluate whether we should get out or not. So it is a much more direct method. Is that okay? So from the readability point of view, I can see how in a short code like this, it doesn't really make much difference. But when you think about, if this chunk of code is not a one-liner, it's a 20-line thing that has its own nested loop and its own nested conditional statement, that means this is also going to be a 20-line piece of code, 20-line piece of code with its own nested loop and nested conditional statement. Then it becomes much more difficult to figure out that, oh, by the time we get here, f has this particular value. As opposed to here, it is really clear because the condition is right after the initialization. So that would be my rationale of why I would prefer the first loop instead of the second loop. Is that okay? So this is not me being argumentative. It is just me saying, in general, if you can choose between a pre-checking loop and a post-checking loop, a pre-checking loop is typically preferred. Is that okay? All right? Okay. So now we got this part figured out, okay? And the other comment was, well, this looks kind of difficult to read, especially just the condition part. So what we'll do is we look at this condition and go like, how can we make this easier to read? Do you guys remember De Morgan's law from the previous class? Maybe? It's also known as a distribution of negation. Okay, so let us go through that again, okay? So the negation of A or B is really the same thing as not A and not B. That's one part of De Morgan's law. The other part is the negation of A and B is really the same as not A or not B. That's De Morgan's law. So in this case, we can, in fact, apply De Morgan's law because we have a negation that is acting on the result of an OR. So we can use De Morgan's law. So once you use De Morgan's law, what you're doing, really, is you're distributing the negation to the inside, okay? And then you are changing the operator from OR to AND, in this case. All right, does that make it easier to read? We don't like the negation, okay? So let's see if we can get rid of the negation at all. So if you don't like this negation, then you can just go in and go like, oh, the negation of an equal to just means not equal to. Okay, I'm going to use this symbol to represent not equal to. And then on the other side, not greater than is really saying less than or equal to. We're done. So that code is equivalent to the original code. It's just that the condition is expressed differently. So are we doing okay so far with this code? All right. So now we have this chunk of code. Okay. So let me highlight which part we're talking about. So we have this chunk of code that is actually doing what this part is doing. In other words, my so-called operation, the operation called find a prime factor f of n, now we know how to do it. So now what you can do is you can copy and paste this chunk of code in place of here, and now your entire program is done. Is that okay? But that's going to complicate the original code. In other words, if you use this approach, then eventually you will still end up with a program that has a lot of nesting, a really long program, with a lot of things that you need to keep track of, which kind of defeats the original purpose of top-down design. So how do we deal with that problem? Well, for now, we'll just say that there are mechanisms to deal with that problem. They're called subroutines, and we will talk about subroutines in this class, but later on. All right, so moving on to this slide here. So basically, it's the same thing, except, this is a nice not equal to. And the top-down design refers to me being lazy and procrastinate and specify what needs to be done instead of how it is being done. Okay, so that's the top-down design part. And then the last section here basically talks about how top-down design is not the only way to write a program. If you need to go bottom-up sometimes, it's fine. Okay, top-down is just one way of getting started with a program. But it doesn't have to be the only way of writing a program. Do you guys understand what I mean by that? Okay. Okay. Let's go back to writing your English Writing 300 paper. Okay. How many times you have an idea, you're doing something, you're washing dishes, okay, and then suddenly, blink, some idea came to your mind, and you go like, oh, this is related to the paper that I'm writing, and then you just kind of jot it down on a piece of paper, stick it to the folder, and you continue to wash your dishes, right? That's bottom up, because you're coming with an idea, you don't quite know where it fits within your paper, but you're putting it into the folder, and then you can file it later. That's kind of bottom up, because it's not from the structure anymore. Your mind just think of something that's relevant, and then you put it there, and then you later on try to incorporate it. That works in programming as well. So there are cases where my own programs are constructed that way, from the bottom up instead of from the top down. So in this particular example, bottom up is going to be working on the code to find the prime factor first. And once we have that mechanism, then we go back and say, okay, now how do we solve the problem of finding all prime factors of a particular number? So we reverse the process. Is that okay? And in practice, in most actual programming, it is a combination of the two. Sometimes you do the top-down design thing, other times you do a bottom-up design. And at some point, you get the whole thing figured out. Do we have any other questions about the approach of top-down design? No questions? Any questions about any specific stuff that we have talked about here, like the mod operator, how we determine whether a number is divisible by another number, or how do we determine a number is prime without having to test a whole lot of potential factors? So are there any questions regarding those? Nope. All right. So if there are no questions about those topics, we are now done. Oops. Okay. Go back. So we are now done with this entire module. So when going back to here, control structure is now done. And we are moving on to a new module called arrays. So now let's go ahead and take a look at the introduction of the concept of arrays. Okay. I just regenerated this like yesterday, so that's why this is kind of fresh. Okay, so the first question is, why do we need arrays? Okay. I can just start with syntax and the concept of an array, but that wouldn't be, I personally need to know why first in order to understand the concept. So I always like to explain, well, why do we need this when we already have variables and all the other stuff? Okay, so I hope this code looks kind of familiar. It's not exactly the same as last time, but it should be familiar. If A is greater than or equal to B, then A is, we use A to update M. Otherwise, we use B to update M. What do you think this is doing without even looking at the caption of the algorithm? Finding the maximum. Okay, very good. Good job. So you guys recognize this code already. So now my new question is, well, how do we find the maximum of 3 variables? I think we talked about that a little bit in this class too. So we look at this code and go like, yeah, we know how to do it, okay? This is one variation of doing it, not the only one. So we can now say, well, if A is greater than or equal to B and greater than or equal to C, then A is the maximum. We'll use it as the maximum. Else, well, then we can determine between B and C. If B is greater than or equal to A and B is greater than or equal to C, then B is the maximum. And then the else of that is, oh, okay, since A is not the maximum, B is not the maximum, who else can be the maximum? It's got to be C, okay? So that's how we can kind of get an idea of, okay, we know how to add one more variable and change the algorithm a little bit and handle that, okay? In other words, if the next question is, what if we have A, B, C, and D, and we want to find the maximum of those 4 variables? You guys probably go like, yeah, I got it, okay? I know how to handle it. What if we have 30,000 variables? Would you still use that approach? How long would that program be? A little bit too long, right? Okay. So then what do we do? Why do you think I use 30,000 as an example? The enrollment of ARC is about 30,000. So if I need to sort anything, if I need to determine the maximum or the minimum of something across all students in this school, then I need something that can deal with finding the maximum or the minimum of 30,000 numbers. Using this approach is not going to be pragmatic. Can it be done? Yes, but I'm not going to do it. If I have an alternative, a different way that is simpler, I'm not going to do it. So now you might ask, okay, so what would the code look like if we use the concept of an array? Not even knowing what an array is. Just show me the code. How short is that? That. Okay? And it can handle any number of variables. 30,000, 50,000, 3 million, same thing. Oh, okay. Now it sounds kind of interesting, right? Because the same pseudocode can now be used to find the maximum of a variable number of variables. Is that okay? So don't worry if you don't know, okay, but what is the bar doing in this code? What are the square brackets? What is I doing in this loop? That's okay. We'll explain that, okay? The idea is it's not long. 8 lines of code can now handle any number of variables. Okay? So are we good so far? Understanding the rationale of why we want to use, or why we want to have arrays. Okay? All right. So now we want to get into the concept and talk about what an array really is. So the first thing is, an array can be seen as one variable, but I wouldn't say an individual variable, okay? So there's a distinction. I can say that A is a variable, which means sometimes I look at the entire array and go like, this is one thing. Move it from here to here. Make a copy of that, okay? But other times, I might want to break it apart and go like, what are the components inside this particular thing that is called an array, okay? So now, we basically say that, oh, okay, so an array can contain components. So here are the properties of an array, some attributes. Every element of an array should have the same type. Now, this only applies to a typed programming language. C, C++, and Java are typed programming languages. PHP, Python, JavaScript are not typed languages. So in those languages, elements of an array can have different types. Yep?
What does that mean, a typed programming language?
A typed programming language means a variable, during the lifespan of a variable, it can only be used to store values of a particular type. Now, what a type is integers is one type, text or strings is another type. So those two are different. So 49 as a value means the quantity of 49. But on the other hand, TAK, my name, TAK, has no particular numerical meaning at all because it really is just literally TAK kind of put together in that order. So that's what I mean by type. So if you're dealing with C and C++, then the array can only be used to store only integers. Every single component of an array can only be used to store integers. You cannot say the first one stores an integer, but the second one is going to store a name, the third one is going to store an address, and then the last one is going to store a zip code. Can't do that. But you can do that with a scripting language like JavaScript or PHP. In those cases, it is not limited. Okay? But since most of you are moving on to cisp360 after this class, so I'm just going to assume that and say that the type of every element in an array must be the same. It's only referring to the type, not the value. Okay? So the first element can be 5. The second element can be 10. The third element can be -60. But those are all integers. It's fine. Okay? Every element in an array has an index, which is basically an ID within the array. Okay? So later on, I'll draw a picture, and it will become clear. The index of the first element is 0. This is strange, because most people count from 1. But in programming, we count from 0 most of the time. Okay? There is a reason why we count from 0, okay, even though it's counterintuitive. But I'm not really sure. Well, actually, in this class, we'll get to see some of that. But there's a reason why we count from 0. But just keep in mind that we always count from 0 in programming. The indexes of elements can only be, they have to be contiguous. So you cannot say the index of the first element is 0, the next one is 10, the next one is 11, and then the next one is 15. They have to be contiguous. In other words, it has to be 0, 1, 2, 3, 4, and so on. Okay? If A is an array, this is just a notation. The bar A bar notation indicates the number of elements in A as an array. Okay? It kind of makes sense because you just look at the 2 bars, like the 2 ends of a line, and then you're just measuring how many things are in between. Okay? The last element of an array A has an index of bar A bar -1. In other words, if you have an array of 5 elements, the index of the last element of that array is 4. Why? Because we count from 0. So the indexes of those elements is going to be 0, 1, 2, 3, 4. Is that okay? So when you have 5 elements, the index of the last element is 4, which is the number of elements -1. And then an element with index I in an array is represented as A square bracket I. That's just a notation. Okay, so now with all of these notations and whatnot, which is kind of abstract, let's draw some pictures. So we'll draw some pictures to kind of get a visual of all of these things. Okay, I don't have the Android up yet, so I'm going to take a look at, well, maybe later. So we'll start up the screen copy program. And get my pen. There we go. All right. And I'm going to move this down a little bit so that we can see the abstract description as well as the picture itself. All right. All right. So before we talk about arrays, we have variables, right? We have variable x, variable y, w, and so on. So you can kind of imagine each variable, each individual variable as a coffee mug, okay? So in the example of finding the maximum of 2 variables and storing the maximum into into M, in that one, we have one coffee mug labeled A, one coffee mug labeled B, and the last one labeled M for the maximum. Okay, so this way when I say, oh, grab the content of that variable. Which one? The one labeled A. Grab the other one. Which one? The one that's labeled B. So we can designate which variable we want to make use of when we only have individual variables. Okay, so is that picture okay? Okay, so now what is an array when we have this concept already? I chose the name poorly because I usually use A as the name of an array. I can always just use something else. That's fine. So we'll say, let's say R, okay? So now we have an array of R, okay? So let's say R is an array of 3 elements. Okay. What does that mean? That means we got a box now. So we have a box. On the outside of a box is the name of the array, which is R. So whenever we refer to R by itself, we are referring to the whole box. If you say, move the box R from here to here, we're moving the entire box, including all of its content. Is that okay? When we say, copy R to another array, that means we're making a copy of not only the box, but also everything inside the box. Okay? But in this case, the box R has 3 coffee mugs inside. So you just kind of imagine that you have an X-ray vision, and now there are 3 coffee mugs inside the box named R. Okay. But now the question is, so I opened up the box, I got 3 coffee mugs. But how do I designate a particular coffee mug inside the box? Because from time to time, I may only want to access 1 coffee mug instead of all the coffee mugs. Is that making any sense? Yep.
The first one that you put into the array is designated 0.
Yep, exactly. So all the coffee mugs inside the box do not have names. They only have numbers. So the first one is labeled 0. This is not, be very careful because 0 is not referring to the value. It is referring to the index. Basically 0 in this case is really just the name of the coffee mug. And then we have 1 and 2. So the box is named R, but the individual coffee mugs only has a number on it. Is that okay? Well, in that case, what do I need to do if I just want to pick up this coffee mug? If I just want to refer to this guy, what is it going to call? What is it going to be called? It is the name of the box, and then in square brackets, the number or the index of that particular coffee mug. Is that okay? So it's just a naming convention, if not anything else. And I think the square bracket thing works out really well, right? Because outside of the square bracket is kind of like saying the name of the box. And then the square brackets themselves is representing the box. And then inside the square brackets is the actual index of which thing inside the box do you want to access. So I think from that perspective, the use of square brackets is actually really, really, appropriate. I don't know whether that was the original intention, but I found a way to explain that so that you can remember easily. So do we have any questions about the convention, basically the syntax of how do we refer to the box, how do we refer to each individual thing in the box, and so on? Any questions about the notation? Well, what about that bar notation thing? So in this case, the bar notation is almost like you're using a measuring tape to say how many things are in this box. Well, so in this case, bar R bar is 3. There are 3 coffee mugs or 3 items inside this particular box. So are we good so far with the notation? So the notations, seems to have graphical elements to it, right? The bar notation is kind of like measuring the width of a box, and then the square bracket thing is like saying the name of the box, which is outside of the square bracket, is R in this case, and then the individual thing I want to access has an index or label of 1. So I go like, okay, cool, kind of cool, but what is this going to buy me? Because I can now say, using the original code, so I can now say, if R bracket 0 is greater than or equal to R bracket 1, then if I want to find just the maximum of 2 variables, okay, M gets R bracket 0, else M gets R bracket 1, and if, that doesn't seem any better. In fact, it's worse. because I have to now type the open square bracket and close square bracket. We're just using more characters for no particular reason. This is not helping. Well, let's think about another way of looking at the index. So the power of what arrays are buying you has to do with what you can use to specify the index. What do I mean by that? It is what you can put inside the square brackets. Okay, what can we put inside the square brackets? Yep.
Different types of variables, so like integers, names.
Anything that comes up to be the integers in the right range. Okay? In other words, what you put inside the square brackets only has to be an expression that ends up as a value that is of integer type and within the range that of, in this case, from 0 to 2. 1 is only one example of such an expression. Is that okay? Okay, what do you mean by 1 is just one example of of what you can put inside the square brackets? If variable I has a value that is between 0 and 2, I can put I in here, or I plus 1, or I divided by 2, and so on and so forth. Okay, so that gives you a lot of flexibility as to which thing inside the box am I referring to. Oh, okay, let me evaluate this expression. The result of the expression tells you what item in the box I want to access. That is the great flexibility that the concept of arrays is going to buy you. Are we doing okay so far with this? Because to identify one coffee mug inside the box, it is no longer a name, it is now a number. And we can compute numbers using expressions. That is what is powerful about arrays. Now is a good time to take a break. So let's get back here by 7:07. That gives you 5 minutes to collect candies. Okay, the recorder is on again, and we'll double check. Yep, so we have been streaming all along. It's just that the audio was off during the break. Okay. All right, so getting back to the flexibility because of arrays. So now there's flexibility as to, oh, we can use an equation, not equation, we can use an expression, we can use calculation to figure out which item do we want to access inside the box. This was something that we never had, we never had the ability to do something like this without arrays. So array is really cool because now we can just say, oh, we can use a loop now. Because in each iteration, if I change the value of I, then in each iteration, I can refer to a different item in the array. Is that okay? Making any sense? Okay. All right. So we are now continuing with the loop concept here. And the first thing is really just a very simple algorithm. And the job of this algorithm is to initialize all elements in an array to zeros. Okay? So how do we do it? We'll read the code first, and then we'll trace it, because I want to show you how to trace an algorithm that makes use of an array. The first line, okay, if you want to read, you can read it by yourself too, because this is the text explanation of everything. But instead of reading it, I'm just going to talk about it. So the first line is just initializing a variable I. Now this variable I is not special in any way. Okay, by itself, it really is just a variable, a coffee mug with a label of I on it. And it is initialized to a value of 0, which means we start with a value of 0. And then we get into a loop, okay? So this loop is kind of the same as the loop that we have analyzed before, except the bound or the condition is no longer just specifying 3 or 5 or something like that. It's saying, well, as long as I is less than the number of items in array A, we stay in the loop, okay? So you do need to know the size of the array before we can run this code. What do we do per iteration? Now, here comes the magic here. The magic is to say, well, we want to store a 0 into one of the coffee mugs in the box. Okay? Which box? Oh, the box that has label A on it. Cool. But which item in the box? Ah, so now we are saying use the variable I, the value in the variable, to tell us which item in the box we want to change. Okay? But remember, I is a variable. And the next line, line 4, is incrementing the value of I per iteration. So the first iteration is going to put a 0 into the first element in the array. The second iteration will put a 0 into the second element in the array. The third iteration will put a 0 into the third item in the array, and so on. Is that okay? So that means independent to the size of the array, these 5 lines of code will initialize every single element in the array to the value of 0. Is that concept okay so far? Yep. Because you might have an array that is needed to store like game score of something. So you want to 0 everything to 0 first, so that you can like count how many times this team has won, how many times the second team has won, and so on. So you want to reset all the counters to 0 first. So there are many applications where you want to do something like that. Okay. All right. So now the next question is, but how do we trace this code? In other words, we know what it looks like. We kind of conceptually understand what it does, but how do we trace something like that? So let's go ahead and use another sheet of this spreadsheet to try to figure that out. Since the pseudocode is here, I'm not going to repeat the pseudocode in the spreadsheet to save some time. So instead, we'll start the columns for the trace. Line number is always there. Comments is needed here because we have a condition to evaluate. We have one typical variable, which is I. Okay, I is just like any other variables. And then we have A, which is an array. So now A is a little bit special because A is not an individual variable. It has components. And in order for this algorithm to work, I have to predetermine what is the size of array A. So let's say, A has 3 elements. So if A has 3 elements, the way I do it is to label it like this. So this is label bracket 1, bracket 2, and then bracket 3. And then what I also do visually is to merge, Alt O-E-M, and merge these 3. So visually, I would merge those 3 cells into one, which means if you refer to A, you're referring to columns D, E, and F. But if you're talking about A bracket 0, then you're only referring to column D. If you're referring to A bracket, I used the wrong indexes.
I was about to say.
Counting from 0. Okay. Sorry about that. There we go. So if we're referring to A bracket 0, we're only referring to column D. If we're referring to A bracket 2, we're referring to only column F. But if you say A, we're referring to all 3 columns. Are we good so far? Okay. Okay, so now let's go ahead and make these columns a little bit narrower, because that makes it easier to read when we trace it. And like that. Line number can be a little bit shorter. Okay. So now we want to specify the precondition. So as far as the precondition is concerned, everything can be unknown. Okay, so we put question marks everywhere, because we are not reading any one of these columns before we change it, and that's why they can all be unknown. All right, so on line 1, that's pretty easy. We know how to do this. So variable I is now starting with a value of 0. And this is supposed to be lowercase I, but it keeps changing to uppercase because the spreadsheet is doing some auto correction. So let me see if I can change that. Nope, that's not the option to do it. Auto correct options. There we go. Correct 2 initial capitals. Nope, do not want to do that. And there's a replacement table, and I can change the replace. Oh, okay. Which one? No, it's already unchecked. So this is already unchecked. It's just that the I is also referring to I as in self, and that's why it's automatically capitalized. So that has to be a localized option. Nope. Exceptions. There we go. Okay. So we just have to get rid of one of the nope. It's not one of those. Maybe it's under replace. It's not one of those either. Okay, well, I'm going to figure it out later. But for now, this is uppercase I because I can't use lowercase I. Okay, maybe if a space, if I put a space first. Nope, doesn't like that either. Okay, fine. I'll wrestle with LibreOffice later on. Okay, we move on to line 2, and then we ask I is less than bar A bar. Is that true or not? Okay, so we know what I is. I is 0. What is bar A bar? The number of elements in the array, and that is 3. Very good. So bar A bar is 3 because we have 3 elements in the array. 0 is less than 3 is true. Very good. Okay. So now we move on to line 3. Line 3 is going like A bracket I gets a value of 0. So now what do we do? Okay. Well, first thing first. Whenever you have brackets in parentheses and whatnot, you go to the innermost part, figure out what that part is, and then you work your way out. Is that right? Same thing here. So you look at the square bracket and go like, well, we better figure out what is inside the square bracket first. Inside the square bracket is just an expression I. Do we know what I is? I is 0. The value of I is 0. So the expression I is also just 0. So A bracket I is really referring to just A bracket 0. Is that okay? So the whole thing is really just saying the left-hand side, the thing that we want to change is column D, because column D is A bracket 0. This is what I want to change. It was unknown previously. Now it is 0, because 0 is on the right-hand side of the assignment statement. All right. So do we have any questions before we move on? Because this is really the big moment of using arrays. Yep.
Why do we make the assumption that A bracket I is the first point in the array?
It's because I is 0. The variable I currently has a value of 0. So when you refer to A bracket I, you're actually referring to A bracket 0. Okay? If you want to think about an analogy, it is almost as if you are, let's say, a postman, okay, and you're looking at an address. Except, the street address or the street number is not written, in a way. It's a little posted, okay? So someone decides and go like, oh, okay, I want you to go to this address here, and then use a post-it and slap it right in front of the street address. So that changes, all the time. So now where you're going depends on what is on that little post-it that is on top of the address. Is that making any sense?
Yeah, so we just,
okay.
Just depends on whether or not I is initialized to a different number at the beginning before you enter the while loop.
Yep. But not before. It is when line 3 executes.
I mean, like when I is originally initiated as a 0 in line 1.
Mm-hmm.
That's how we knew when in line 3.
That is correct. Yep, that is correct. But line 3 always refers to the value of I at that moment. At the moment that we run the code on line 3. So we'll see that, okay? So we'll see that later on. So we now move on to line 4, because line 4 is really just after line 3, which is I gets I plus 1. So I goes from 0 to 1. And then where do we go? This is the while loop. Back to line 2. Very good. Okay, good job. So line 2 is reevaluating the condition, and it is still true because I has a value of 1 at this point. Bar A bar is still 3. 1 is less than 3 is true. Okay? And then now we end up with on line 3 again. So this time I has a value of 1. Okay? So the expression I is giving you a value of 1. So that means inside the square bracket, okay, inside the square bracket here, that I is really just saying 1. So A bracket I is referring to A bracket 1 this time. Where's A bracket 1? A bracket 1 is represented by column E in the spreadsheet. So that is the one getting changed. Getting changed to 0. Very good. And then we move on to line 4. Line 4 is adding 1 to I. I goes from 1 to 2. And then we go back to line 2 again. I is less than bar A bar. It's still true because I has a value of 2. 2 is less than 3 because bar A bar is 3. Are we still doing okay so far? Okay. And then we go to line 3 again. And this time we kind of know why we have to go to column F to update it, because I has a value of 2. So A bracket I is referring to A bracket 2. And that's why column F is the one that is getting updated. So that one is now getting a value of 0. We go to line 4. We add 1 to I. I goes from 2 to 3. We go back to line 2. We reevaluate I is less than bar A bar. This time I is 3. So is bar A bar. 3 is less than 3 is false. And that's why we get out of the loop. There's nothing to do after the loop, so that becomes the post condition. Is that okay? But did you guys realize what the flexibility is once we use arrays? The same line of code on line 3, so when I highlight all the line 3s, they are now updating a different thing in the array. Is that okay? I think it's really cool because this gives us the ability to use an algorithm and use mathematics to determine which thing do we want to look at again or which thing do we want to change again. And that is really, really important because most algorithms really need this particular mechanism to work. Are we good so far? All right. Okay, so let's go ahead and try to come up with a new algorithm, okay, that's not actually in my notes. So what we'll do is we will try to come up with an algorithm to determine whether an array is sorted or not, whether something is out of order or not. Okay, how many people are okay with the concept of what is being sorted or in order? Is that okay? All right, so I'll give you some examples. So the numbers like 1, 3, 14, 17, 20, and 22, that is in order, okay? But if I give you like 1, 14, 3, 17, 20, 22, it is not in order anymore, okay? Now the other one, which is 20, 22, 20, 17, 14, 3, and 1, is also in order, but it is a different order. Is that okay? So now we want to write an algorithm. So we'll say write an algorithm to determine whether an array is sorted in quotes, non-decreasing order. Okay. So now I'm giving you a kind of exercise and say, well, can you write me an algorithm to determine whether an array, the elements in an array, are sorted in a non-decreasing order. So non-decreasing order is almost like increasing with one little difference. Two elements can be the same, okay? Is that okay? So we'll just go through some examples. Do it by hand first, okay? So we'll say, what about 1, 3, 3, 17, 17, 20, and 22? Is that sorted in a non-decreasing order? Yes. Yep. Okay, cool. What about 1, 3, 1, 17, 17, 20, 22? That is not in order. What makes it not in order? These two are not in order, right? Okay, so what did you do to determine whether something is in order or not? You have to compare, but what are you comparing? Okay, so what I'm gathering is we're comparing adjacent elements in the array. In other words, we are comparing the first versus the second, and then we compare the second versus the third versus the fourth, and so on. And we can get out as soon as we find one pair that is not sorted. We don't need to go any further. In other words, in this case, we first start with 1, 3, that's in order. We have to look at the second pair, 3, 1. Not in order. We can now get out immediately because we can say, hey, if one pair is not in order, the entire sequence is not in order. Is that okay? All right, so we know how to do it by hand now. So now the question is, can we write an algorithm to do it? So once again, yep, go ahead.
So could we then have compare like the array and the integer, and then compare it to the integer, the array integer plus 1?
Mm-hmm. Yep. So there's a +1 inside the square brackets. Okay. Yep. So now we want to construct the algorithm once again, step by step. So we're not going to go like, oh, this is line 1 and blah, 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 this is line 15 and and sequentially do that. We will write this algorithm in steps. All right. So once again, we got 3 choices. I'll be talking about a sequence, which means, oh, we are just doing a whole bunch of assignment statements in a particular order, and we're done. What do you think? No. Okay, because we have decisions to make, right? So anytime you have decisions to make, like we want to get out now, that's a decision, okay? Or we want to continue in this case, that's a decision. So every time you say, we got a decision to make, it means it is not a sequence. All right, if it's not a sequence, we have 2 additional choices. It can be a conditional statement. It can also be a loop. What is the difference between the 2? A loop. Well, we have to choose between a loop and a condition, but you had your hand up, so you go ahead.
A loop because we have to compare multiple variables.
Exactly. We don't know how many times we have to do something. if you cannot predetermine how many times you have to do something, it is most likely a loop. Okay? If it is a one-shot thing, it's like, well, it's one or the other, and you only have to answer and ask a question once, it can be a conditional statement. But if you have to ask a question over and over again, it is most likely a loop. Yep?
Won't this be a loop with a nested conditional statement, though?
Not exactly. Not exactly. Okay. So we want to now, so we know it's a loop, okay, which is great. Because knowing it's a loop, we can now say the algorithm is a loop of some kind. Whenever you have a loop, except for very, very few occasions, you have to exit the loop. Okay, you have to say, when are we getting out? Okay, so when are we getting out of this loop? There are two reasons to get out of this loop. Go ahead.
When you know that it is in non-decreasing order.
Okay.
Or if you know that one value is greater than the next.
When you find adjacent elements that are out of order. Okay, very good. So we'll just write that. Okay, so we'll say we can exit when we confirm the array, the entire array is sorted, or we find adjacent elements that are out of order. Okay. Is that okay? And you can see that, but this doesn't even look like pseudocode. We cannot write this kind of stuff in a real program. You're absolutely right. But this is a starting point, okay? So it means when you're thinking about how to solve a problem using pseudocode, try not to think in actual code, okay? Think about the meaning, the semantics of what you're trying to express. The syntax comes next. It is the concept that is the most important. Are we doing okay? All right? So we look at this and go like, okay, we don't really quite know what to do with this. Because, I'm not really sure how we can express this. Okay, you look at this and go like, well, let's try to express this in a more pseudocode way instead of a statement, kind of way. Yep.
While whatever the first iteration is, or the first index is less than or equal to
Okay.
index plus 1.
Very good. So we have comparison. Okay, so we're going to throw in that. Okay, so every little idea that we have, we'll throw this in. In other words, we are using the kind of bottom-up approach right now. We're just saying, okay, let's brainstorm. If we can figure out something that might be useful, we just kind of throw it in. Okay, because that seems kind of to be important, right? Because if something is in order, that is true. Okay. But at the same time, we have to say, but how do we refer to these elements? It becomes a notation issue now. How do we designate and spell out this element versus that element? Well, we kind of need to know the name of the box, right? And something else, okay? So we have to say now, assume we are using an array called, give it a name, okay? That's all we're doing. Because otherwise, we'll say like, which array are we talking about? Well, it is that array with the name of A. Okay. Well, if that is an array with the name of A, and we are comparing elements of the array, so that means we are comparing something like this with something like this, right? Because we are comparing two elements of the array. Each element can only be using this notation to specify it. Is that okay? Okay, so we'll just say that, okay, that's my second revision of the code. We have resolved a few things by giving a name to the array, and also at the same time, okay, and also at the same time identifying that we need to somehow use the less than or equal to thing, and we also need to somehow use the indexing kind of thing, okay? So now the next question is, how do we know which two elements we are comparing? We know we have to compare two adjacent elements, but which two?
You have to initialize the first one as the 0 plus.
So we need another variable, right? We need a variable to tell us which two elements are we comparing. Okay, so now we basically say that, okay, let's use another variable for that purpose. So now we say assume we are using I as a variable to specify which two elements are being compared. Is that okay? All right, so now we go down to this code, and then we just specify, okay, a bracket I specifies 1. What about the other one? It would be I plus 1. Very good. Okay. Now this is really cool because it gives us the ability to specify this element versus the one after that, because we can use an expression to calculate the index of an element. Is that okay? Because I really want to point out, what makes arrays so cool. Because one can use an expression I, the other one can use the expression I plus 1. Very cool. But now we go like, wait. This condition doesn't seem right, because this is what we want, right? We want it to be in a non-decreasing order. So when a bracket I is less than or equal to a bracket I plus 1, it's actually a good thing. It's not out of order.
We need to add an else. A bracket I is greater than or equal to a bracket I plus 1, and then we need to change the assignment of a bracket I plus 1 to I a bracket.
What about this? What about just adding a not to it? In other words, if if this is specifying something is in order, the negation means something that is out of order. Is that okay? Yep. All right. So we are going somewhere. So let's go ahead and save this one and move on and use a copy to move on. Do you guys see how I'm not really writing the entire algorithm in one shot? I'm just, I specify, well, today is Halloween, right? So we start with a skeleton. So we start with a skeleton, and then we start to add a little bit to it. We add a little bit of flesh. We add some tendons. We add something to it, and then we add some more to it, and then we add some more to it, and then we add skin, and then we add hair, and so on. That's basically what we're doing with programming. Okay. We're starting with something that's really kind of abstract and go like, ooh, that doesn't look like code at all. And we are incrementally trying to change and refine the algorithm so that it looks like code. All right? Okay. So now we got a few problems because, hey, we are referring to a variable I. We better know how to initialize variable I. In other words, what should it start with? 0 seems to make sense, right? Because we want to compare the first element with the second element. The first element has an index of 0. The second element has an index of 1. Seems to work. So we say we initialize I to 0. Okay, cool. We start from the beginning of the array. Well, if that is the case, now we try to tackle the most difficult problem, which is how do we confirm the entire array is sorted? Okay, go ahead. Yeah. Yeah, because there was another hand back there.
We will use that same line for the initialization algorithm we used before, which is while I is less than
bar a bar.
Bar a bar.
Okay, so we know it has something to do with bar a bar. Okay, do you want to add to it?
It's basically the same thing.
Okay, so we'll look at that. Okay, so we say I is less than bar a bar. Okay. But that's a problem, okay? In fact, this is a really good problem to have because it forces me to explain something that is really important. So if you look at this evaluation, okay, what if I is exactly bar a bar minus 1? So think about that scenario. What if I is exactly bar a bar minus 1? Then this condition would be, it would be true, okay. What about this condition here? Then we'll be comparing a bracket bar a bar minus 1 with a bracket what? Bar a bar. It does not exist. Okay, very good. Okay, so let me just write it down here, okay? So if I equals to, okay, I use double equal to kind of emphasize that we are specifying equality. If I equals to bar A bar minus 1, then this condition, okay, when I say this, let me be more specific. Because I don't like people when people use the word this, that, he, or she, because I want things to be more specific. So now it will say more specific. So this condition will evaluate, will become, okay, A bracket, not the negation of A bracket, bar minus 1, less than or equal to A bracket, bar, close bracket. Is that true? In other words, it's just a matter of substitution, right? So we know that I is bar minus 1. We know the first element of the comparison is A bracket I. So I just put this I, okay, or the value of this I into this I here. Then I get this part here. Is that okay? And by the same token, I'm taking the value of I, and then I put the value of I into this place here. And because the minus 1 and the add 1 will cancel out, I end up with bar A bar, right? So that means if bar A bar is 3, I will be attempting to refer to A bracket 3, which is a problem. Because remember, the indexes start with 0. So if your array only has 3 elements, the indexes will be 0, 1, 2. There is no 3. So now the question is, but what if my code is actually written this way? What's going to happen? Does anyone want to know? Or do you want to wait until CISP360? Okay, so the answer is, it depends. Don't you like those answers? So it depends. If you're running this code in C#, Visual Basic, and most scripting languages, even Java, okay, it will give you what we call a runtime error. It will say, oh, your index is out of bound. It is not supposed to be 3. And it will give you a line number, and your program is going to stop. It's not a crash, okay? It is just giving you a runtime error, telling you what the problem is, on which line, and it just stops, which is good. In C and C++, it's not going to stop, okay? It will go to a certain memory location where this is the location where if A bracket 3 did exist, it would have been there. But since it's not there, it's really just using a memory location as if it is A bracket 3 and use it as if it is A bracket 3. So that means you'll be comparing A bracket 2 to some value that you have no idea what it is. Sometimes it is greater than or equal to. Other times it's not greater than or equal to A bracket 2. So now the behavior of your program becomes unpredictable. You don't know which way it's going to go, which means you can test your program 20 times, it works okay, and then the 21st time it doesn't work anymore because it has to do with how memory is initialized in this case. Is that okay? So so the bottom line is do not index out of bound in C and C++. And the worst part is it doesn't check it for you. In C and C++, there's no checking. The compiler and the programming language does not check whether you're indexing out of bound. If you do, then your program becomes quote-unquote unpredictable, which is bad. Okay, so watch your indexes when you're doing array indexing in C and C++, and make sure that in your code, your logic does not index out of bound. All right, so that's the best way I can put it in this class without looking into how an array is actually organized in memory and stuff like that, because that's really in CISP 310. Are we doing okay? All right. So do not try to index out of bound. But in this case, we are, in fact, indexing out of bound because we know that when I is less than bar A bar minus 1, we are not going to fail this condition. which means this condition will be evaluated, which is problematic. Okay, so what if I change this to, okay, let me copy and paste it. Okay, copy and paste. So what if I change this to this? Do you think that's going to work? So if I is less than bar a bar minus 1. Oh, wait. That's stay in loop condition. So we have to say greater than or equal to. So when I is greater than or equal to bar a bar minus 1, we don't have anything else to compare. So we need to get out. Is that okay? So that means I have to change the other one to, just change this to greater than. But we cannot wait until it's greater than. We cannot wait until it's greater than or equal to just bar a bar. We have to use bar a bar minus 1. As soon as I reaches bar a bar minus 1, there's nothing for me to compare anymore. Let's get out. Is that okay? Okay. So this looks okay so far. What is left to do is to specify what do we do per iteration. I starts from 0, but somehow it's going to end up as bar a bar minus 1. How can it go from 0 to bar a bar minus 1 if everything is in order? In other words, okay, going back to the more graphical way of looking at this, in other words, how do we move from comparing these two to compare these two? What do we need to do to I so that initially we compare a bracket 0 to a bracket 1, and then we compare a bracket 1 to a bracket 2? Yep. Yep. So we just have to increment I in the loop. So per iteration, we're really just adding 1 to I. Okay. Good observation. So we just put here and say I gets I plus 1 for each iteration. All right. Well, we got most of it done. So now we only have to decide, well, do we want to use a repeat until loop, which looks kind of like this? We check the condition afterwards. Or do we want to use a pre-checking loop where we check the condition first before we increment I? What do you guys think? First? Check the condition first. So we want to use a while or pre-checking loop. That makes sense. Okay? Why does it make sense? What if the first two elements are out of order already? Then we don't want to add 1 to I because we want to compare a bracket 0 to a bracket 1. Right? Okay. So that means we can now refine the algorithm just one more time. Well, maybe there's one more time to do it. I'll explain why I said that. Okay, so now we say, okay, we know it's a pre-checking loop where we specify while, some condition do, and then the end part here is just going to be end while. Really, it's just a phrase to mark the end of the while loop. But what do we put here? In other words, we were able to specify the exit condition. Now we need to specify the condition to stay in the loop. What do I do? Negate it. Yep. So we just have to say the negation of whatever we have here. Okay, so stash it there. And just combine the lines because it doesn't look good. There we go. All right, and then we get rid of this because we now have specified the condition of the pre-checking loop. All right, so we got this code. And we look at this, go like, looks kind of ugly. Okay, we got a lot of knots, So most of the time the knots can be removed, okay, one way or another. So once again, we're going to use what? Which rule do we use to transform it so that the knots kind of go inside the conjunction or the disjunction? De Morgan's law. So we use De Morgan's law because we have a negation on the outside of a or. Okay. I'll do it step by step, so this way, when you review the video, you can actually see how it is done. So we take this knot, okay, from the outside, and then we move it to the inside. So we put a not here. And this is going to be funny because it's going to say not, which is fine. Okay? Is that okay? But we have to change the or to an and. The Morgan's law distributes the not to the inside, but you have to change the operator. Is that okay? So looking at this and go like, well, we now have more nots than before. I thought we were trying to get rid of the nots. Right? Well, let's try to get rid of some nots here. Not greater than or equal to. Less than would do, right? So okay, so we change it to a less than, and then we get rid of the not. Oh, okay, that looks cleaner. What about the other one? Not. Negation of a negation cancels out, so we just say that, right? So now we get rid of that, and let's see, I'm just matching up the parentheses. Yeah, that's matching up fine. Cool. Looks nice now. Does it look nice? Okay, looks better, right? All right, so but we still want to double check and make sure it still makes sense, okay? So now we are asking, do we want this loop to basically say as long as I is less than bar a bar minus 1 and a bracket I is less than or equal to a bracket I plus 1, continue, move on to the next pair, and keep comparing. Does that make sense? Seems to make sense, okay? Then we look at it from the other perspective, which is, well, by the time we get out of the loop, what can get us out of the loop? Well, this is a conjunction, which means if at least one side of the condition is false, we get out of the loop. Does it make sense? Okay. So what does it mean when I is no longer less than bar a bar minus 1? What does that mean? What is the actual meaning of that condition? That means we have reached the end, and yet we could not find something out of order. That also automatically means that the entire array is sorted in order. Cool. What about getting out because of the second reason? What if the second part, the first part is true, but the second part is false? What if a bracket I is less than or equal to a bracket I plus 1 is false? What does that tell us? What is the meaning of that?
Something's out of order.
Okay. Yep, something is out of order, okay? And should I get out of the loop because of that? Yes, because we have a conclusion now. We have an answer of whether the array is sorted in order, so we can get out. Once we have an answer, we can get out. Is that okay? Okay, so there's only one little thing I have to add here. I just have to say that if I is greater than or equal to bar a bar minus 1, which means it's not less than, then we can conclude the array is sorted. Okay? Else, we can conclude the array is not sorted, is not in order. And if. Does that make sense? Now, what do I want to do when it is sorted? I don't know. I mean, nobody told me what to do with the result. Okay, so I can only say that, yeah, over here I can conclude the array is sorted or the array is not sorted, but what I need to do about that is up to somebody else. Is that okay? Any questions about this pseudocode? From line 70 to line 81 is the pseudocode that I'm referring to. So let me just highlight it so that you guys can kind of focus on just this pseudocode. Are there any questions related to this pseudocode? Yes? Are you referring to this condition? Yeah. Okay. So I start from 0, right? Yeah. And then bar a bar is, let's say it's 3, okay? Let's say we have an array of 3 elements. So bar a bar is 3, 3 minus 1 is 2, so we're comparing 0 to 2. We are comparing the count minus 1, not comparing the value of the array items. Yep. Okay. Any other questions? Any questions about the process of how we get here? How we derive the algorithm from something that was really, really, really vague. Like this. That's the original algorithm. This is the first thing we kind of notice is like, oh, we can get out when blah, 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 based on the observation of the 2 examples that I have presented here. Are there any questions about that process? No questions? All right. How many people think that over time, okay, not necessarily like in this semester, but over time, you do not need to go through all of these revisions first in order to get to the bottom, to get to the actual code? Yep, over time you can do it. But within this semester, I would say, yeah, don't be too ambitious. Okay, so don't beat yourself up if you cannot go straight to the last portion and go like, yep, this is the pseudocode. So here's the next question. Well, we got the pseudocode now. How much work is involved to turn this pseudocode into actual code? Not much, exactly. Well, but what if I were to turn it into C++ code? How much work is involved?
A little bit more.
Yeah, a little bit. What if I were to turn it into... oh, I can do it in assembly just like that in my mind. What if I were to turn it into, say, JavaScript? About the same. About PHP? About the same. What about Python? About the same. What about Visual Basic? About the same. In other words, most of the work of programming has nothing to do with the syntax of the programming language. It has to do with everything else that you have to do before you get to the syntax of the programming language. I would kind of put it this way. The syntax or the difference of the syntax of different programming languages is kind of like, when you drive a car, how Toyota puts the headlight, control on the stalk on the left-hand side, and then the Buick has a little lever, to do that, and then Volkswagen has a little turning knob thing, to control the headlight stuff. It's kind of like that. Okay, how much time does it take in order for you to from getting used to driving a Buick to driving a Toyota? At the most, a few hours, right? Okay, that's the difference between a programming language from the next, usually. Okay, so if you count really awkward programming languages like Lisp or Prolog and something like that, then it's a little bit different. It's kind of like motorcycle versus a car. Okay, but if you're comparing C, C++, Java, Python, Visual Basic, PHP, and so on, we are really just switching brands, and sometimes it's just within GM. Oh, you're driving. Oh, I was about to say Pontiac, but Pontiac is no more, right? So it would be a comparison between a Buick versus a Chevy. Okay, how different are they? Not a whole lot. That's between C, C++, and C#. Okay. Well, what about between Python and C++? Well, that's a little bit different, so it would be kind of more like a Honda versus a Buick. Do you have to go to DMV and get recertified because you switch from a Buick to a Honda? I hope not. Okay? Okay, wait, but so in this analogy, what about this part of using pseudocode and try to figure out the logic of the code? What is the equivalence of this part in terms of driving? Is it actually the learning of how to drive, learning all the rules of the road, learning how to slow down the car, how much to slow down, how much to turn around the corner. That's the difficult part. But once you get that part done, switching between cars is relatively easy. Is that okay? So that's why I use pseudocode, because I don't want to get stuck with a particular syntax of a particular programming language. I don't even want you guys to focus on syntax at all. I just want to focus on the ideas of how to get to an algorithm. So are we doing okay so far with these concepts? Okay. So switching back to the notes here, okay. So whenever I present an algorithm, like this one here, I always present an explanation of what each line is doing. So the next one is searching for a value in an array, okay. So I start with just the text of what needs to be done, and then I actually present the pseudocode to do it. Kind of the same thing, same journey, okay. So what you might want to do, okay, since I have already used a particular example in class, so what you might want to do is to kind of try this one by yourself, okay, and just say that, well, if I want to see if a particular value k is in an array, how would I do that using a loop and using the concept of an array? Okay, it doesn't have to be right. Okay, give it a try. Use the kind of same process that we went through in class today, and try to step by step, figure out, what the algorithm should look like. Okay, there's no right, there's no wrong. I'm not going to collect that, and grade it, but I want you to go through that process. The reason why I'm not collecting it and grade it because it's really hard to grade. So that's really honest, and it's really hard to grade because most of you is likely to make a mistake somewhere, okay? And so now the question is, how much partial credit should I give you? Well, it depends on where the mistake is, what the mistake is, and so on. So it means it really is difficult for me to evaluate and give you partial credit. Now, on the other hand, if the grading is only saying whether it's correct or not, I can easily do that. But I don't want to give you guys like all or none, okay? So I would much rather not grade this one and then let you guys kind of go through the process so that on Friday, when we come back, we have 2 ungraded assignments to do now, right? Because we have the one that is outstanding, the one that I kind of gave you guys today, the pre and post condition thing, and then we now have this one. Now this one is easy, okay? People who want to kind of give up and go like, okay, I give up, I just want to know what it is, just scroll down. I mean, the answer is down there. Okay, and that's the other reason why I don't want this to be a graded homework assignment, because I don't want you guys just to copy and paste, turn it in, I'm done. Because I really want you to just genuinely use some time, see if you can derive the algorithm, okay? Now, let's say you run into some obstacles and go like, I have no idea how to proceed from this point on. Bring that in class on Friday. Okay, if you don't feel like, I don't want to raise my hand and tell the entire class I cannot proceed because I did not know, no one in the class could proceed either, right? That usually happens. Then you can send me an email, okay? Send me an email and say that, well, I'm kind of stuck with this version of the code. I can't go on any further because I don't know how to proceed from this point. That's fine, okay? Give me those examples so I can use those examples to understand where people are getting stuck at, then I can try to explain how to proceed from that point. Is that okay? So I'm asking you to help me do my job to help you. Not. Is that okay? All right. Well, we're 5 minutes short, so I want you guys to kind of have a chance to collect some more candies. Just try not to run over people who are actually collecting candies. That's my major concern on Halloween. At least it's not raining tonight.